And
Good.
so if we're ready, then I'd be very happy if Yair wants to tell us all about tidal disruption events and what's happening with them. Now there's more than a few.
Okay, sounds good. Thank you very much.
Thank you.
Thanks for organizing this conference, Łukasz and everyone. It's great to be able to attend, even in this format. So I'm happy to open the session on the transients in galaxy centers, or at least partially about that, by talking about tidal disruption events. So a tidal disruption event is what happens when a star gets too close to a supermassive black hole. If it gets to within what we call the tidal radius, this is the radius at which the tidal forces from the black hole, so the gravity on one side of the star compared to the other from the black hole, is stronger than the self-binding gravity of the star, and the star then is no longer bound to itself, and it gets disrupted around the black hole. And if this happens outside of the event horizon, then we might be able to see something happening from it. Now, this is a complicated problem to model, but it has a lot of potential, because if we can see something from it, then it can be used pretty much as the only way to study quiescent massive black holes beyond the nearby universe. So black holes that are not actively accreting all the time. And it can also teach us about accretion physics, radiative processes, and also stellar dynamics around supermassive black holes that are responsible for getting the star into those disrupted orbits in the first place. So there's a lot of potential in studying these events, but first we have to understand what is happening in order to interpret the emission. So you see on the left-hand side the classical picture from Martin Rees. The star comes from the left, it gets disrupted at this tidal radius, and then half of it is unbound and escapes, and half of it is bound and returns to the black hole to get accreted. But the picture in reality is a lot more complicated. This is just one simulation of this effect that doesn't take into account all of the physics, and you see that you just see by eye that it's much more complicated, and there's a lot of different physics happening at a lot of different scales, which makes this difficult numerically to model. So the question is, should we see any light coming from these events? And the initial expectation was, well, yes, once the material comes back, it will form an accretion disk, it will accrete, and accretion disks emit light because there's heat, and this energy is dissipated in the form of light. And the light in accretion disks around black holes comes out in the X-rays. So it was quite surprising when the first TD was found in optical. I mean, TDs were found in the X-rays, but the first optical event was found. It was kind of surprising. This was a flare in the center of the galaxy. It looked kind of like a supernova at first sight, but it's more luminous than a typical supernova. Its spectral features are different than a typical supernova, and it didn't cool down. It stayed hot. It stayed blue and hot at around 30,000 Kelvin for hundreds of days, which supernovae can't do. This didn't answer most of the properties we expected from TDs. It was not at the right temperature. As I said, it was hot, but not X-ray hot. It was not at the right radius. The black body radius was much larger than expected from the tidal radius. The amount of energy was lower than expected. The temperature was constant instead of evolving, which you expect from an accretion disk. And there was this mystery that there was no hydrogen in this event, which is also strange. So how could this be a TDE? Well, since then, there have been many more found. The light curves are quite similar. There are a few events that are fainter and more rapidly evolving, which obviously we're not complete to, so we still don't know their intrinsic rate. And also spectroscopically, we have now this atlas of events, and many of them, you see the top three here have no feature around H alpha. They show no hydrogen, they only show helium-2. But some events do have hydrogen. So we're still trying to understand this diversity of features, but they're all in galaxy centers. They're all non-active galaxies. We'll touch upon the galaxies a bit later. So they are not some kind of supernova. They are very likely TDEs. But then why are they emitting this in the optical and not in the X-rays? So one idea was that there's all this material around, either from the disrupted star or it was there before, that can reprocess the emission from the accretion disk. So the accretion disk indeed emits in the X-ray. This gets reprocessed, and we see it in the optical on the other side. And models of, if you take an accretion disk and if you take an X-ray source and you run it through reprocessing material, you can actually explain, depending on the radius of the reprocessing material, you can create this helium feature and turn this hydrogen feature on and off, because basically it depends if the photosphere is where the hydrogen is ionized or not. And so you can explain the spectral features, you can explain the temperature that you see and the radii, because the black body is formed in the reprocessing material and not in the accretion disk. But there is another explanation when you do the simulation with general relativity. So here the star just got disrupted, and you're seeing half of the material of the star flying away, half of it is returning to the black hole. Okay, it will pass again around the black hole, but a few things come out of these modern simulations. One is that the shocks produced here, where it passed in the closest point to the black hole, are not enough to dissipate energy and make it circularize into an accretion disk immediately. But the second thing you see is that the material collides with itself. So the part that went through the return to the black hole once is colliding with the part that's on the way in, and this generates shocks. And these shocks can dissipate energy and produce emission. So the idea that Zvi Piran and his collaborators put forward is that the emission that we're seeing is not from the accretion disk. It's not from the accretion disk being reprocessed, but it's from these outer shocks caused when the material collides with itself. And they can explain, again, the temperatures we see, the radii we infer. And the additional bonus is that they explain how the material circularizes to form an accretion disk, because the shock that forms here in the closest point to the black hole turns out is not enough. It does not dissipate enough energy to circularize the material and form an accretion disk, but the outer shocks can do that. So it explains, so in this case, it suddenly means that we're not seeing the accretion disk at all. We're seeing the process that happens before the accretion disk is formed. And of course, this has implications to interpreting the emission that we see and deriving the black hole parameters that we are seeking to derive. So now we have two explanations for the optical emission that we see, either reprocessing material or these outer shocks. And we are trying to see if we can distinguish between these observations. So here's an event where we're seeing the optical decline and then the X-ray rising. So we thought, okay, this means that we're seeing the accretion disk starting to form after the outer shock. So the optical was the outer shock emitted from the outer shocks. And then it dissipated energy and the material circularized and started to form an accretion disk, and you see the X-ray rising from this newly formed accretion disk. But it can also mean that the accretion disk was always there and we were seeing reprocessed emission, but the reprocessing material was thinning as time goes by and it became transparent. And this is just the transition between us seeing the reprocessing material and then seeing inward into the accretion disk that was always there and was powering this light curve from the beginning. So there is some more evidence that we might be seeing accretion disk responsible for the optical emission, and this is an event published recently where you see this feature in the H-alpha line, which has this double peak profile, which is modeled as an emission from an accretion disk. So this double peak profile is because half of the disk is moving toward you and half is moving away. And this is what the disk looks like in the spectral line. And Hung et al. Infer from this that the disk formation took place promptly after the most bound degree return. And so here it strengthens the picture that the emission that we're seeing is from the accretion disk itself being reprocessed. But it could be that both things are happening. And here are two events where you see a double peaked light curve with the idea being that maybe the first peak is indeed powered by these outer shocks and the second peak is powered by accretion. For this event on the left, 2018 FYK or Gaia 18 CYC, you see that during the second optical part, the X-ray increased. These triangles of the X-ray suddenly increased. So again, this could mean that accretion has started at that stage. And the interesting thing about that event is there was these iron features in the spectra, which are interpreted to be, you get iron features when you have X-ray being reprocessed. So it could be that the X-ray was actually already there. The accretion disk was already there. It was just being reprocessed. And then when the X-ray goes up, these iron lines go down. So indeed, this favors the picture that, the X-ray was always there, but then the material that reprocessed it got transparent, and now we're seeing directly. Other evidence that the accretion disk forms eventually is from very late time UV and optical observation. So you see here several TDs and the decline. The dashed line shows the expected decline of the TDE. And these points show that the UV flux at late times is sometimes much higher than this expected decline. And this could be remaining flux from a longer lasting accretion disk that was formed eventually. So I think we're collecting very nice observations, but I think the jury is still out into what exactly we're seeing and when. And
10 minutes, yeah.
Thanks. And so we don't yet know exactly what the emission we're seeing, where it's coming from, or how to decompose it into the two components if they are both there together. So obviously, you know, as a good observer, I would say that we need more events and more observations. The spectra, getting clues from the spectra is also a bit complicated. I'll just say this rapidly, that the spectral lines don't always tell us about the dynamics. They can be related to optical depth effects. And so in many events where we see the lines getting narrower, this doesn't mean that the velocity is moving slower, but the density is changing. And we see this in many events, but then interpreting it is now also complicated because it could be due to dynamics, or it could be due to optical depth effects, and it could be due to a combination of both. And I will also just briefly say that events where we do see the narrower lines, we see a much more rich array of species, not just the hydrogen and helium we saw in the first event, but we see a bunch of other lines now that we also need to interpret. Okay, so I'll just say one word, that most of the TDEs are found in a weird type of host galaxy called an E+A or post-starburst galaxy. And we're not quite yet sure why or what this tells us, but this is definitely teaching us something about stellar dynamics in those galaxies and what causes stars to get disrupted in the first place. So I'll just put up my summary that we have new observations of the established TD class, but we still have a lot of questions. Most notably is, what are we seeing? Where is the light coming from? Is it the accretion disk or reprocessing material, or some combination of both? The spectral class also seems more diverse than we thought. There will be more talks about this later. And we are still not quite sure what causes this peculiar host galaxy preference, but we have some clues that it might be due to the mass concentration in the center of these galaxies. So whereas progress, it has been fast, but we'd like it to be faster. And for that, we need to find more events. The current rate is about a few, used to be 1 per year. With ZTF now, it's more like a few to 10 per year. But we'd really like to help find more in Gaia data to try and see what we can do to help solve this problem of identifying transients in galaxy centers. So I'll end there, and thank you very much.
Thank you very much. I see, I'm looking for questions, and we have one from Milena. If you could unmute yourself, please, Milena.
Hi, hello. Thank you for a very nice talk, Yair. I have a question. I didn't get it. I was actually wondering, in spectroscopy, when you see double peaks, that you actually understand as it may happen that one part of the feature comes from the outer shock and the other comes from the accretion. Do they behave differently? Okay. No, so first of all, hi, Milena. Good to see you. Thank you for the question. No, so the double peak profile is interpreted as just an accretion disk. If you're looking at an accretion disk from the side, then part of it is rotating toward you and part of it is rotating away. So this part will be blue shifted and this part will be red shifted. Okay. So you can model this quite well, and there are also relativistic effects that you can model. And so you can know about the accretion disk, how big it is and stuff like that. So the double peak is just telling you this is a typical feature of an accretion disk itself. So if you see the double peak in the optical, it's really telling you that the accretion disk is powering that emission, or at least part of it. So that feature was actually a bit more complicated. It was probably a double peak plus a regular single peak feature. So it could be that part of it is outer shocks and part of it is accretion disk. Makes sense. Thank you.
The next person with the question was Michelle Dannefeld.
Yes,
please.
Hello, yeah. I was wondering how you can initially identify a TDE candidate when you have a lot of objects to classify. Is there a color index or something? Is a first classification spectrum enough to identify it, or do you need to follow it for several days before being sure?
Yeah, this is the million-dollar question that we keep asking ourselves and refining. So, we're in this stage where we have like a few TDEs. So we think we know, okay, they are all very blue. But then we don't want to bias ourselves. What if there are red TDs? You know, we don't want to completely bias ourselves. But then, of course, 90-something% of things you classify in a galaxy center are type 1a supernovae. So it is an expensive endeavor to classify everything. So we are really thinking about these criteria. Obviously, it has to be in the center of a galaxy. As far as we know, it's blue. All of the TDs that we've seen are blue, but now again, because we're using this as a real way to select them, and we're not sure how much of this is a selection effect and how much of this is intrinsic. Typically, if you have a first spectrum and it's blue, you still don't know if it's a young supernova or if it's a TD, but if it remains blue for a while with a second spectrum later, then it is very likely a TD. If we see these helium-2, strong helium-2 broad feature, then this is very characteristic of a TD. So we're kind of still building our classification criteria and hoping not to introduce biases in this way. But if you want to be complete, you have to be ready to classify many type 1a supernovae.
Okay, thank you.
Thank you very much. Thanks for the questions. We're going to move on now to Nada Hanek. Nada, you've got 5 minutes. So I'll give you a warning when you only have 1 minute left. Okay? We don't hear you.
Yeah, I have to unmute myself. Apologize.
And we've lost your screen now as well. I'm afraid.
Okay, yes. So I think now you can see it, right?
Yes, we can.
Okay.
Take it away.
Thank you. So hello, everyone. I'm Nada Ihanets. I'm currently a PhD student at Astronomical Observatory University of Warsaw. And from recently, I'm also a support astronomer at Isaac Newton Group of Telescopes in La Palma. So today I would like to present so-called bone fluorescence flares. I would like to start with flares from the centers of galaxies. So why do we want to study flares from galaxies? And the answer is to study the properties of the black holes. So to do that, the flare has to be associated with the central black hole. And Gaia alerts have so far discovered, so 7% of all the alerts are classified as nuclear transients. The biggest problem is that it's really hard to say whether or not, what is actually a nucleus of the galaxy. So the distance from the center. As you can see on the images, on the top one, the galaxy was fairly close, and the localization of the event, we could assume that this is actually in the nucleus of the galaxy, and this turned out to be TDE, what Yair was talking before about. However, in the lower one, this blob is in fact a galaxy. However, because it's so distant, it's really hard to say whether or not this localization happened in the nucleus of the galaxy or not. So in nuclear alerts, we have there are a few possibilities that can be, so either AGNs, tidal disruption events, or as Yair mentioned in one of his answers, there's also a possibility, and there's a huge chance that transient that occurs in the so-called nucleus, invisible nucleus, is actually a supernova, and it's not related to the black hole itself. And the last events are so-called boson fluorescence flares, which were first mentioned 2 years ago in Nature paper by Trackenbrot et al. So I would like to talk about these specific events and the new Gaia alert, the recent Gaia alert that was found. So Gaia 19AXP was discovered in March 2019. It showed 1 magnitude rise in known quasar at redshift 0.374, so it was fairly distant. The Gaia light curve showed some minor variability. However, it didn't show any huge flares. The same happened if we look at the light curve of Catalina's survey, which was observing this galaxy between 2005 and 2013. It does show some variability. However, again, there is no big 1 magnitude or more rises. So this galaxy was observed with SDSS, and it does have archival spectra and was classified as narrow line Seyfried 1 galaxy. So soon after the detection, the classification spectra was observed, and it showed so-called Bowen fluorescence lines. We started multi-wavelength follow-up to get as much information about this event as possible. So in the last year and a half, or almost now 2 years, we've observed the event in near-infrared, optical, and UV light. So near-infrared we got from not optical from multiple sites. The main one was from LCO. ZTF also
1
observed
minute, Nada.
Okay. ZTF also observed this event, and we got nice bolometric, we were able to calculate bolometric luminosity and temperature evolution. There was no radio source detected in 2 arc seconds, and there was, however, X-ray only 260 days after the peak. We also see some mild infrared observations from NeoVice, though both near infrared and show some delay in light revolution. Spectroscopically, the main focus is this Bowen fluorescence, which occurs because some Lyman alpha photons excite certain stage of oxygen and nitrogen, and this is particularly strong in oxygen 3, and then nitrogen and helium. So we got a fairly good, really good follow-up, and we were focused on to see the evolution of the lines. And as you can see, with the latest spectra show decrease in helium-2. So this is part of a broader class, so Bowen fluorescence flares. So far we have, there are 3 published classes, and as you can see, there are different redshifts. The magnitude of the flares are different. However, here on the right side, we have the host-subtracted flares. So all of them show approximately 2 magnitude rise. So they have, not only they are similar in spectra, they also similar in this. They are for sure not TDEs. So even though they have similar black hole masses and certain similarities to a TDE Bowen class, which was introduced in Valvence in 2020, the light evolution is much slower, and also the spectroscopic evolution is smaller as in TDEs. So in summary, the Bowen fluorescent flares are a new class of supermassive black holes related flares. The main points are the UV optical frame from the nucleus of the galaxy, and then in spectra strong oxygen 3, nitrogen 3, and helium-2 line emission lines. So that's it.
Thank you. Thank you very much. And I don't know if there's one quick question. Then I'll ask Simon to start sharing his slides. If you could stop sharing, please, Nada.
Yes.
And we'll move on quickly. Please take it away, Simon.
Yep, thank you. Can you see the presentation?
We can see the presentation. We can hear you well.
Okay, thank you. Yeah, so one of the topics I am interested in is, excuse me for 1 second, is quasar variability. In particular, how you kind of compress such a nice light curve as you can see here. So this is 20 years of data for one quasar in the OGLE survey. How do you basically, maybe not compress, convert such a nice light curve with many points into a small number of parameters that you can then compare to the physical parameters of quasars? Yeah, but I will tell a little bit more about this in a second. But before that, well, I just want to say that, you know, I have worked at the Warsaw University Observatory for 10 years. Well, I'm based at the same floor as Łukasz and his group is. So Łukasz and his collaborators have been asking me questions about quasar variability. And you can see some questions. I don't know if these are the exact questions, but they were asking me questions about, you know, can AGN mimic other types of variability? Can AGN be smoothly rising by 1 magnitude within 1 year or something like that? And I basically didn't know the answers off the top of my head. So I decided basically to simulate AGN light curves as they would be seen in Gaia. So how do you simulate AGN light curves in Gaia? Well, you need a number of things. First of all, you need to know something about the variability of quasars. So if you have a light curve like this one, such a light curve needs to be converted into a small number of parameters. And you can do it in a number of ways. One of them is to directly model the light curve, let's say with a damped random walk. So we can model the light curve. You get 2 parameters, the time scale and the amplitude. Or you can calculate the power spectrum, which will look something like this. So it has a slope, then it bends and flattens, and there is a frequency at which it bends, and there is some amplitude here. Or you can calculate the structure function, which is in the top, in the bottom right panel. So it has a slope, then the structure function bends and it flattens, and there is a time scale at which it flattens. All these things are interconnected, and well, we just have 2 or 3 parameters to deal with. In the case of the damped random walk, the slope of the power spectrum here is fixed to -2, which is actually not the case in the real data. Or for the structure function, the damped random walk has a fixed slope to 0.5. Yeah, so what I did, I took 9,000 quasar light curves from the Slow Digital Scale Survey, and I calculated structure functions for them. And from analyzing structure functions, you can get a number of parameters of variability. One of them is the amplitude at long time scales, which is this SF infinity. It's the amplitude here. Then you have the time scale, which is the decorrelation time scale, which is somewhere here. And then you have the slope of the structure function or the power law, which comes in here as beta. So from the data, you can actually measure the autocorrelation function of the data, which will be used to simulate quasar variability in the Gaia data. Then what you need is some relations between the black hole mass, basically between the physical parameters of quasars, which is the black hole mass and the bolometric luminosity, to the variability parameters. And for the simulations I will show in a second, I used these equations. And there are catalogs with black hole mass and the luminosity for hundreds of thousands of quasars available. So I used the available data. Another thing that you need is how to convert, let's say, the SDSS data to the Gaia magnitudes. So this is a plot. This is a color R minus G for quasars as a function of redshift. And what you can see is basically it wiggles a little bit around 0. So you can just directly take SDSS quasars and turn them into G magnitude. And then for the last thing that is necessary to simulate light curves is the photometric noise. So this figure is actually based on von Leuven DR1, Gaia DR1 paper. And so from that paper, I derived this relation between the noise and the magnitude. There are figures in the year 1 data and the year 2 data papers where we can see that the completeness of the data drops very quickly after some magnitude around 20. In the year 1 it was 19.8. In the year 2 is 20 point something. But I use this this curve to simulate the light curves. Yeah, and the simulation, this is, well, you don't need to read that, but the simulation is very simple. So your magnitude is the signal of variable quasar plus the photometric noise plus the mean, because the signal this varies around the mean, which is 0. So your next point is your previous point times the autocorrelation function. So the tau is one of the parameters that we measured, and we have this noise part where we have the amplitude and again the autocorrelation functions. So we have all the ingredients to run the simulation, and I did that for 60,000 quasars. So they were converted from the SDSS magnitudes and variability parameters to the Gaia parameters, and I looked at the light curves. So some light curves are presented here. So these are 3 typical light curves, not the best light curves, typical light curves for such simulated quasars. Obviously, the cadence in Gaia depends on where you look at the sky. I used a simple cadence, 2 points separated by a couple of hours, separated then by 30 days. So there are 2 points every 30 days. And so these are typical light curves for quasars at a redshift of 0.04, 0.4, 1.2, and 2.6. And this is how a typical light curve for a quasar may look like. Then I ran some other additional codes on the data. So this is the peak-to-peak variability for the simulated quasars. And this is the table with the data length. So if your data length is 10 years, then your mean peak-to-peak variability for quasars brighter than 19.8. That was my cutoff, is 0.6, and basically 14% of quasars should have variability higher than 1 magnitude. And depending on the Gaia time span, you can read off how variable objects you can have. Yeah, so the solid line here is the curve for 10-year long data, and yeah, so the most common peak-to-peak variability is 0.6 magnitude. Of course, peak-to-peak magnitude is something different than the dispersion of the data. You should divide this by roughly 2.5 to get the dispersion. So this should be roughly 0.2. The dispersion, the typical dispersion in the Gaia data in the simulated quasars is 0.2. Yeah, but let's discuss some contaminants or some fake objects. So I looked through some of the data. I didn't look through all 60,000 light curves, but I looked through a subsample of the data. So I found some objects that may mimic, let's say, microlensing. So we have 2 light curves here. They obviously wiggle a little bit at the baseline, but well, you can fit a simple microlensing even to the simulated quasar data. The chi-square per degree of freedom is 1.9 here and 1.5 here. So you can find in a simulated data events that will resemble microlensing. Yeah, you can find something that resemble supernovae. Well, there are obviously some wiggles, so this may not what we want in supernovae, but apart from that, you know, you have this nice shape that may resemble microlensing, and this is another one. And yeah, and I was getting several questions about long, slowly, smoothly rising variables. Can they be, I don't know, TDs or something? So I didn't know. So, well, I found a bunch of light curves that do nothing at the baseline and then they slowly rise. And, you know, if we assume that we are at this point and the gray area is something we don't know yet, so we don't know what will happen in the future. So we may, well, this may be triggered as an alert, but once we know the data which are not yet observed, well, it may not be what we want. So for example, this is a curve that is slowly rising, and this could be whatever at this point, but then it just does like this AGN thing. Okay, thank you.
Thank you very much. I was staring at your fake light curves, and they look remarkably like the light curves I am staring at every day of quasars that we see with Gaia. So it's very impressive. But I noticed in your light curves as a function of redshift, one of your first sets of 3 fake light curves, that the amplitude decreases significantly with increasing redshift. It's where you showed 3 example light curves.
Yeah.
And so then that asked me about the function or into your models for the light curves. How have you come up with the parameters that define the variability as a function of wavelength and therefore redshift?
Yeah, so these are parameters taken from the SDSS quasars. So, you know, I was trying to do one-to-one match. So if the quasar is at a redshift of 2 in the SDSS, I took these parameters and used them for a quasar, for the same quasar in the Gaia data. So it's like,
okay.
Yeah, I didn't have to use any like additional functions. I just took one-to-one parameters basically.
But if we're looking at a high redshift quasar, we're essentially looking at the rest frame UV light. What do we know about UV variability of quasars?
Yeah, so the shorter the wavelength, the higher the variability. Yeah, but on the other hand, with redshift, the light curve is stretched, so it looks like it's smooth. It looks like it's more like smooth or something.
Yes.
Yeah.
Yeah. Okay. Thank you. Do we have more questions? If not, I'll ask the next speaker to start. If you could stop sharing, Simon.
Yep. Thanks.
And I'll ask the next speaker, who's Morgan Fraser, to begin sharing slides. There we have. We see Morgan's slides. Morgan, we don't hear you. I don't know if you're speaking.
Okay, can you hear me now?
Yes, we can.
Okay, yes. That's good. And you can see the slides?
Yes, we can.
Okay, brilliant.
Morgan, you have 15 minutes. I'll give you a warning once you've used 10.
Okay, thanks, Simon. So thanks for the opportunity to talk. In 15 minutes, I'm going to try and talk just very briefly about 2 things. The first is something I wanted to show how Gaia data for supernova can be useful in the context of a larger follow-up campaign. A few years ago, I had a lot of ideas about how Gaia data would be useful, and it turned out that some of the ways it would be useful are things that I didn't anticipate, and some of the things I thought it would be good for, it wasn't for. So it's interesting to see how it's turned out to be useful in practice. So the object I want to show is a transient called 2016 GABU. So to give some context, there's a class of transients, possibly supernovae, possibly not, that appear to undergo a long period of variability, having very bright outbursts. So you can see a kind of light curve here for a set of these transients going back 10 years, and you see all these points or detections of them. And then they're followed by a very, very bright event that looks a little bit like a supernova, and then they fade away again. And there's about, nearly 10 of these transients known now. And 2016 GABU is another member of the class. And the possibilities are that, you know, these are supernovae where you have some sort of eruptive mass loss beforehand, like a supernova from a very massive LBV-like star. Or alternatively, it could be a non-terminal eruption, so not necessarily a core collapse. If you look at the spectra of these objects, they're dominated by circumstellar interaction. So this is for, you know, 5 different members of the class, including 2016 JBU. And you can see they're shown here at different phases in the light curve. So these are spectra taken just around about here, just before peak brightness. These are some spectra taken around about here, so kind of after peak brightness. And here are spectra taken about a year after their main event. And in all phases, what you see are narrow, relatively narrow, so less than 1,000 kilometer a second emission lines. So this is caused by photoionized material in the circumstellar medium. And they're a puzzling class of objects. So there's sort of contradictory data. So you don't see any evidence for nucleosynthesized material. You don't see evidence for production of nickel-56, which you would expect if it's a core collapse supernova. On the other hand, they're really bright and really energetic. So obviously supernova. So 2016 JBU, we've got 2 very long papers led by a student of mine, Sean Brennan. I'm not going to go into them in detail, but I just want to focus on one little detail of how Gaia data was really useful here. So this is a light curve. So zooming in on this region here. This is a light curve collected for 2016 JBU by us and our collaborators. And each one of these colors is a different photometric band. So you see we have everything from UV with Swift through to sort of mid-infrared with Spitzer and WISE. So it's an absolutely huge data set. And you might say, well, all this monitoring, why do you actually need data from Gaia? Why is Gaia useful? Well, it turns out Gaia supplies one really critical point in the light curve, and that's right here. So this gap in the light curve here, you can see there's a broken x-axis here. This is due to the seasonal gap when the transient went behind the sun. And when 16 JBU was going behind the sun, its light curve was kind of going down like that. And then when we picked it up again, it was brighter than we would have expected. So what happened? Now, with a sort of follow-up from the ground with, you know, particularly a heterogeneous set of observatories providing data in different filters, you mightn't be confident that, you know, what you're seeing isn't simply an instrumental artifact. You know, maybe your photometry is not as good as you thought it was. You know, maybe this is a sort of mismatch between filters. The advantage of Gaia, and we picked it up a little bit earlier when it came from behind the sun with Gaia, is that you have very, very stable and precise photometry, which allows you to be confident of a single data point. So we can say unambiguously, what's happening is the light curve is decreasing, and then it's brightening again and resuming its decline. So without the Gaia data, we couldn't be as confident of this result. So for me, one of the really nice things about Gaia is it gives you very precise, you know, a few hundredths of a mag photometry, even at, you know, 20th magnitude, that if you see little flickering in the light curve, you can know that that's real. So just to finish up on this, what causes this rebrightening? Well, if we look at the light curve, so this is again the light curve again without offsets between the bands, you see this rebrightening in all the filters, but you only see it clear. You see it most clearly in the Gaia data, which is in kind of pink color here. If you look at the spectra at the same time, remember these spectra are dominated by all these narrow emission lines. If you look, the strength of the helium lines goes up around about the same time as this rebrightening event. So these helium lines are non-thermally excited. So this is actually evidence for luminosity energy produced at a shock. So this is increased interaction with circumstellar material as a cause of this. Okay, so great. We've got, you know, a transient dominated by CSM interaction, and now there's a little bit more CSM interaction. Who cares, right? However, we know when the CSM interaction is happening. We know that, you know, we can measure the velocities of the material. We know this is happening, you know, 200 days or 150 days after this peak here. So we have a time, we have velocities, we can work out how far out this CSM material is. So this actually allows us then to start to get a handle on the geometry of the system, and with a lot more information, put this together and make a model where we say, okay, there's a disk of CSM here and a further out kind of wind region and so on. So one data point from Gaia can actually be quite critical in unlocking the physical nature of a transient. So that's the first thing I wanted to say and to show. The second thing I wanted to talk about very briefly was companions to galactic supernovae. So this is some work I've been doing with Douglas Buber, who's now at Oxford. So the starting point for this is that we know the majority of massive stars are in binaries. So, you know, probably upwards of 80, 90% of massive stars are in binaries. And in fact, most of these are you know, sufficiently close that the binary system will interact. They'll lose mass, they'll, you know, transfer mass to each other. Now, for a massive star binary, eventually the primary will explode as a core collapse supernova. And then the secondary, less massive component will either remain in the binary, so it'll remain bound, and that'll presumably give you a high mass X-ray binary, so a neutron star and some massive star. Or alternatively, the binary will be unbound, and that companion will be ejected from the system as a runaway. So stars going around each other, star 1 explodes, star 2 flies off. So with Gaia, can we find these former companions to galactic supernovae? Well, this is what we tried to do. And we looked at the nearby historical supernovae and the very youngest nearby supernova remnants. And it turns out for the Crab and for Cassia, because they're so young, if there was a binary companion to the star when it exploded, it would basically be at the center of the explosion, and people have looked for that, and it's not there. Vela, on the other hand, is about 11,000 years old. So there's a region, a respectable region, where you have to search to find a companion. So, you know, this is a remnant itself, seen in X-rays, this circular thing, and you know, it's sort of 5 degrees across. We're only interested in the very center of it. So let's zoom in on this little box. And now we see a slightly complicated looking optical image. So I'm going to talk you through all the different things you see here. So first of all, in the top right.
10 minutes, Morgan.
Thanks. In the top right, I've plotted, this is actually X-ray flux from the neutron star. So there's a known neutron star in Vela. And you can see it's got this sort of this funny shape. This is actually a bow shock around the neutron star as it moves through the interstellar medium. And you can track back that neutron star, and you can say, well, 5,000 years ago it was here, 10,000 years ago it was here, 15,000 years ago it was here, 20,000 years ago it was here. So if the supernova exploded, let's say conservatively, between 5 and 20,000 years ago, it would have exploded somewhere along this line. Okay, so that's where the explosion happened. The next thing we need to know is how far a companion could have traveled in, you know, order 10,000 years. And to do that, we turn to some population synthesis models. So here we've taken a whole grid of binaries, different masses, different initial separations, and we basically look how fast do you eject the secondary after the supernova. And this is color, and this is ejection velocity. And what do you see? And the darkness is just density. The number of models that fall in that region. What you see is that most things are actually ejected at very low velocity, less than 50 kilometers a second. So going back to this, then we can say, well, we can plot 1, 2, 3 sigma regions where we expect to find a companion. So this is a 1 sigma region where we expect to find a companion. It's got 2 sigma, 3 sigma. So 99.9 whatever % probability, if there is a companion, it won't have gotten outside this outer region. And now what we've plotted, now we've got a region to search. We can simply look at what sources are at the right distance. So that's what these blue points are. Anything marked in blue is a star that's at the correct distance and inside the right region. And now we have the final bit of information we can use from Gaia, and that's the kinematics, so where those stars are going. So for each one of those, we track back their trajectory, and we see, do their past trajectories potentially intersect with the past trajectory of the neutron star. So for example, you can see this star here. The green lines show where it was between 5 and 20,000 years ago. And what you probably can't see very well is just about one of these over intersects the black line. So there's a very, very small possibility that was the companion, but quite unlikely. This one, you know, the same, it's got a crappy proper motion. This guy, however, in orange, which is our best candidate, looks like it intersected with the trajectory of the neutron star just about the time it was supposed to explode. So this is a very good kinematic candidate for the former companion to the Vela supernova. Plotting it on a HR diagram, it lies down here. It's faint, it's red. And unfortunately, this is the point at which our story ends. Because it's 20th magnitude, and we would need to get some high-resolution spectroscopy. You might expect to see some chemical peculiarities. You could get atmospheric parameters and so on. Unfortunately, we got time, but then ESO was closed down due to COVID. So we'll have to try again now in the future. So I think I'll finish up there. I did have one other really exciting thing I wanted to say. So in Gaia DR2, also in the same paper, we looked at the distance to the crab, because you see the crab pulsar, and we got very excited because we thought the crab might be much further away than everyone thought. But then we looked at Gaia DR3, and it turns out it's back at 2 kiloparsec. So okay. Sometimes Gaia takes away. Okay, that's everything I have. Thanks.
Thank you very much, Morgan. I see a question from Łukasz.
Hi, Morgan. What is the fraction of supernovae exploding in binary systems? What do you feel?
So theoretically, it should be high, right? Observationally, we have found very few. In fact, this is a little bit of a puzzle. If you look with this, if we say, you have the crab, Cassie, you have 87A, you have potentially Vela now. If they don't have companions that are what we expect, that's surprising. So one possibility could be that you form a lot of dust inside the supernova remnant, and that enshrouds the companion. Extragalactic searches for companions have also been quite hard to do, because you have a bright supernova remnant for a long time, which will outshine the companion. So it's observationally it's hard, but potentially it's quite interesting, because you can, well, you should pollute the surface of the companion with metals from the supernova ejecta. It also allows you to better constrain the evolution of the progenitor. So you can, you know, see, well, if the secondary ended up here, where must the primary have been? But I mean, I would say more than half of them should have binary companions, but observationally, we don't see that.
Okay, thanks.
Can you stop sharing, please, now, Morgan? Many thanks. And if Mateus, our next speaker, could start sharing.
Yes, just a second. Sure. Now, Do you see my screen?
Yes, and we hear you.
Okay. Hello,
You
everyone.
have, sorry, Matthias, you have 5 minutes, so I'll give you a warning when you have 1 minute left, okay?
Okay. Hello,
Thank you.
everyone. My name is Mateusz Broninkowski, and I want to talk about my search for overluminous transients in Gaia alerts using photometric redshift catalogs. This is mostly a recap from last year, plus an attempt to tell you what's new and what else I found. But to those of you who weren't present last year, so basically what I am doing is I am searching for candidate hosts of Gaia alerts in a galaxy catalog that uses photometric redshift of those galaxies to estimate their that uses photometric data to estimate their redshift. And using that estimate of redshift, we can then find if an alert belongs to a particular galaxy, and then if we find that it belongs to a particular galaxy, we know the redshift, we know the distance, we can calculate the absolute magnitude of a particular Gaia alert. The catalog that I am using is the galaxy list for the Advanced Detector Era, or GLADE. And from there, I select the brightest alerts and search for candidate superluminous supernovae, which I have to then verify by hand. So previously, last year when I presented, I found the following 3 candidates. I found Gaia 18 AFG. I found it to potentially be an alert with a magnitude of minus 23.07. However, the separation from its host galaxy was relatively large, so this one has a small caveat. I also found Gaia 16 BUD to have a magnitude of minus 21.37. And however, this particular alert was also found, or its host galaxy was also found in another photometric redshift catalog called WISE-X Supercosmos Photometric Redshift. However, that earlier in my research, I found that catalog to be very unreliable and to give very wildly varying estimates. So I think, or I find that GLADE is more reliable, and thus the figure of minus 21.37 magnitude is more reliable. And I also found Gaia 16 BFC, which appears to be a superluminous supernova at minus 20.30 magnitude. Since then, since my last talk, I have mostly analyzed all of the alerts that occurred during 2019 and 2020. I found Gaia 19. Among them, I found Gaia 19 EYX, which you can, which you should be able to see on the right, along with its host galaxy. This is a superluminous supernova, as far as I found. However, its host galaxy also has a known spectroscopic redshift. It turns out that the spectroscopic redshift is just 1% different than the photometrically estimated redshift, and thus I believe that this is a decent confirmation of or proof of concept that the method I am using can produce useful, meaningful data. And the Gaia 19 EYX thus is a confirmed in my opinion, confirmed superluminous supernova due to the fact that it has a spectroscopically known redshift, or at least its host does.
1 minute left, Mateusz.
Okay. And I have yet to, Up next, I have yet to analyze the some of the alerts from the -21 magnitude to -20 magnitude range. However, a quick look. So far, I have found that at least 4 superluminous supernovae that were confirmed via other sources, like spectroscopically, were found in this sample. So there is much promise that my method will find some more superluminous supernovae in this magnitude range. And thank you very much. And I await your questions.
Thank you very much, Mateusz. I'm looking to see if we have any questions for you. Pending that, I'll ask you a very quick question.
Yes.
So you have 4 candidates here that are found with your technique. Have any of them had spectroscopic follow-up and classification?
Well, sadly, no, because I run this on historic alerts and not on alerts that are coming out day to day. Sadly, we didn't have the information that, hey, this is a candidate superluminous supernova, and we might need a spectroscopic follow-up. So sadly, these don't have follow-up.
But then this is good for the future. So you'll find more for us and give us advance warning.
Yes, I hope
future.
So.
Okay, that's great. If you could stop sharing now, and
Okay,
I'll ask Benny to start sharing once you've stopped.
In another screen. How do I?
Right.
How do I stop sharing? Okay, thank you.
I think you're
You've
good.
stopped.
Hi. So, can you
see
hear
your
me and can
slides?
you see my slides?
We hear you. Yes, very well.
Okay, great.
You
All
have
right.
15 minutes, and I'll give you a shout after you've used 10 of them. So you
Okay,
know
great.
you have 5 minutes to wrap up.
Thanks. Okay, so hello everybody. I want to show you today some fresh results from our attempts to resolve the mystery of changing look AGN with responsive follow-up observations. This is work that is done, it's observational work, so naturally a lot of people are involved. Some of them are listed here. And we've been hearing this morning already about many, many new exciting types of, I would say, newly identified types of transients related to supermassive black holes. So Yair gave us an overview of tidal disruption events. We also heard from others about, let's say, normal and some more extreme quasar variability. This is dramatic variability of already known quasars. This is done in repeated imaging of Sloan quasars, etc. We have some yet to be understood nuclear transients. You can see an example here. Some of them saturate close to the Eddington limit, which is very interesting. But today I'm going to focus mainly on changing look AGN, this class of sources. You can see it here with this example light curve. We're talking about variations which could be happening on timescales of months, years. This is just the photometry, but what changing look are actually defined to be are accreting supermassive black holes, so AGN, which show dramatic changes not just to their brightness, but specifically to their spectral appearance. Okay, so we will see a few examples soon, but something in their optical spectra or X-ray spectral energy distribution changes dramatically. And so the name changing look implies that if we were to look at them before and after the transition, we would classify them differently as far as AGN classification zoology goes. So let's see how this, what this means in the optical regime. So in the optical regime, changing look AGN are simply systems which show the appearance or disappearance of the typical blue continuum and the broad emission lines that we know in quasars. And you can see examples here. This system here by Rano et al., 2015. You can see it in 2 epochs. First, in 2003, you can see this blue continuum and the famous broad emission lines. In the Balmer lines in particular, we're talking about thousands of kilometers per second here. This was 2003. And then in 2015, this quasar continuum and broad emission lines disappeared. You can see here in the insets that the spectrum has become completely dominated by stellar features from the host galaxy. Another example here on the left, again, spectra taken years apart, in this case, a decade apart, different generations of Sloan. The quasar was on with blue continuum, broad emission lines, then 2010, it turned off, and so it remained for quite a few years. I should note that the term change in look AGN was also coined, or originally coined, in the X-rays, and there the distinction is a bit different, but it has to do with significant changes to spectral shape in the X-rays, suggestive of changes to the column density along the line of sight. So these are just two examples, and there are a bunch more X-ray examples. We're now talking about large samples that are being collected of such sources from repeated spectroscopy, again, separated by years. And if it wasn't clear up till now, you can see here examples of systems which turn off, which I already showed you in the previous slide, but also systems which turn on. And again, just as an example here at the top left, an early Sloan spectrum shows this system to be galaxy dominated, the host galaxy dominated, with no broad emission lines, and then a later spectrum sees all these broad emission lines and the blue continuum. So again, we have now dozens of examples of each sort: turn off, turn on. And so the question is, what drives these changes? And the two basic ideas are that these changes could be driven by changes in the accretion flow, or changes to indeed the obscuration along the line of sight. And when we think of the central regions of an AGN, of an actively accreting black hole, we should be having these kind of physical components in mind: the accreting black hole, the accretion flow, and then several regions, distinct regions of ionized gas. First, the broadline region with clouds or gas moving in thousands of kilometers per second and separated by tens of light days away from the black hole. And then the narrow line region, which is much further out with centuries, and actually much more than that, of light travel time to it, much lower density gas and much lower velocities. It's marginally bound by the black hole. It's actually already kind of interacts with the galaxy. And we may also have some dusty clouds along the line of sight, maybe from the famous AGN Taurus, maybe not. So the ideas for changing look AGN are, first of all, that you can have one of these dusty clouds just moving in or out of the line of sight. So you will have, again, the broadline region obscured and the continuum itself obscured, or maybe revealing itself. And the challenge with this is that it takes more than one tiny cloud to cover the whole system, okay, to hide the entire BLR. And in some of these changing look AGN that I showed you, we see no evidence whatsoever for variability in line of sight obscuration. The other explanation would be a drastic change to the accretion flow. So, for example, in this low state, the accretion flow is very weak, definitely in terms of its ionizing radiation. And then something happens to the accretion disk. There is a flash of UV light. The continuum light travels directly to us. It also travels to the broadline region. It reaches it, and after several tens of days, and only then it gets reprocessed into this broadline emission, which then travels to the observer. So what we expect from this scenario is some sort of a sequence where we see first the blue continuum going up, and only after a certain delay, after a lag of several months, I would say, we would see the broadlines popping up. And so the question is whether this could be confronted directly with observations, and the answer is yes, at least in this event that we caught changing look in the act. So this event, 1ES 1927 plus 654, was a well-known narrow line AGN. Actually, it has rich literature because its X-rays are a bit funky. And so it didn't do much in terms of variability for many years, and then it suddenly was caught up, rising by a factor of 40 in the optical and also in the UV, I should say, within a month. And this is very extreme for quasars, for any AGN, as we've heard in the previous talk in this session by Simon. So it has this sharp rise and then a slow decline. And what we did with this event, we started monitoring it spectroscopically. And I will show you now a time series of optical spectra, most of them collected by the Las Cumbres Observatory network of robotic telescopes. And time is going up here in this plot. You see, for reference, the historical optical spectrum taken back in 2001, where you see only narrow emission lines and no blue continuum. And after the flare was detected, the first few optical spectra we obtained already showed a blue quasar-like maybe continuum, but still no broad emission lines. And so it remained for several months. And then when we continued our monitoring, our spectroscopic monitoring, with data coming in sometimes several times per week, we see this emergence of broad emission lines, particularly broad H alpha, broad H beta, very similar to what we see in broadline AGN. And if you're not convinced that H alpha, broad H alpha appears all of a sudden, you can see it here in this inset. So eventually the system got to a point where the spectrum looks exactly like an AGN, but there is this gap, this lag of about 3 months between the peak of the UV emission and the appearance of the broad emission lines. And this lag is exactly what we expected qualitatively in the scenario I showed you earlier, but it's also fully consistent with what one would expect for the size of the broad line region in AGN, which is known from scaling relations which are based on reverberation mapping. So in other words, it seems like in this event, indeed what happened is that there was a flash of UV radiation, which we saw almost immediately in the imaging, of course, in the monitoring itself, but also spectroscopically in the appearance of the blue continuum. And then this ionizing radiation reached the broadline region after a few months, and then we're seeing the reprocessed radiation. If you need any further conviction that this is the case, here are the numbers. This is the light curve in terms of the imaging of the optical and UV photometry. And then at the top panel here, the broad emission line equivalent with in red H alpha and in blue for H beta, they peak several months after the UV has peaked or the UV optical has peaked. So in this event, it seems like this scenario where we have some enhancement in the accretion flow, light travels to us directly from the continuum from the central engine, but only after some delay from the broad lines. This is confirmed. We've managed to resolve the sequence and to confirm the scenario. So this is great. The problem with this...
10 minutes, Sven.
Yeah, sure, no problem. There are other issues with this event which are not as nicely understood, and I just want to show you how complicated things can be when you start taking high cadence multi-wavelength data. First of all, I already showed you the panel on the left. This is the UV and optical light curve, but I would also like to draw your attention to the X-ray light curve, and we have monitored this source with several facilities, which you can see in the legend. And actually what happened to the X-rays, they did not go up at all. They actually went down by 3 orders of magnitude after the UV peak. Again, with some delay, more consistent with the broad emission lines popping up. After going down by 3 orders of magnitude, the hard X-ray flux actually got back to historical levels. But it's not just the flux. If you look at the panel on the right-hand side of the slide, you see that the X-ray spectral energy distribution, so this is energy in keV, and this is just an indicator of the flux in funky units that X-ray astronomers really love to use. You can see that the spectral energy distribution is all over the place. So just to guide you a bit, this is the historical level kind of back from 2011. And then after we started monitoring, the source visited basically all the other data series you see in this plot. But the consistent picture we're seeing is perhaps that the X-ray emitting corona has disappeared, was destroyed by the UV flash, and then maybe reformed when the UV radiation went down. And this possibility is entertained in this recent paper by Claudio Ricci. Now, this is kind of what happens if you look at the X-rays over timescales of many months. Actually, when you look at it on timescales of hours, and now I'm showing here a wonderful light curve from NICER. So this is a high cadence soft X-rays. You see these pulsations of a factor of 2 or 3 within hours, and this, to be honest, we really can't explain. So still a lot of things going on in this fascinating system. So to conclude on this system, we think we understand what happened with the ionizing flux traveling outwards and igniting the broadline region, but there are still some open questions. For example, what is the origin of the dense gas? Was it always there, just waiting to be illuminated, or did it arrive freshly with the same batch of gas that ignited the whole system. Which brings us to the maybe most interesting question: what ignited, what initiated the whole event? Could it have been a TDE in an AGN, so a star crashing into an already existing accretion disk, kind of perturbing it in a very significant way? And there's some recent papers about this, and we will hear a lot more about this exciting possibility in Tzvi Ran's talk after the break. So all this was for this one very interesting event. It's of course not the only event. We're trying to systematically chase more and more alerts, more and more events. I'm showing at the top part of this slide one example, which is unfortunately not a Gaia alert. This was a ZTF identified event followed up by IPESTO, identifying it as a broadline AGN. And actually, when you look back to archival spectroscopy from the 6DF effort, you see again that over many years, we can't tell exactly when, in this case, it developed broad emission lines. We're not so sure about the continuum in this case. Archival data is tricky, but definitely it used to be a narrow line system. Now it's a broadline system. Gaia is, of course, great for providing alerts. So we're monitoring that too. It's a great opportunity here this week to say thank you to everybody who is involved in the Gaia alert system, and especially for these very handy comments that I highlighted here at the bottom, which really draw our attention very efficiently to AGN and quasars that are doing crazy stuff. This is a good cue for us to go and use our capabilities, our facilities to follow up on these events. So, we're using mainly the Las Cumbres network, which eventually for spectroscopy boils down to two telescopes, one in the north, one in the south. And we've already heard earlier this week that there are some challenges with the Gaia, with Gaia being complete to certain transients, particularly in the centers of galaxies. So I know it's a challenge. Again, highly appreciative to all the efforts, but it's very hard. My point is that it's very hard to conduct a complete survey of such events given our follow-up facilities and the way the alert system goes. So what we're trying to do now, what I'm involved in, is to also conduct a sort of a complete spectroscopic survey. And one way to do it is Sloan 5, which has started taking data this past fall from the north. So it's going to be an all-sky multi-epoch spectroscopic survey operating from the well-known Sloan facility in the US, but also a new facility in the south in Las Campanas. We're going to do both Milky Way, but also, of course, extragalactic science. I hope we will be open to some input from the community as far as target of opportunity programs. And the plan, as you can see here in this summary, summarizing table from the white paper, is to detect hundreds, possibly thousands of these flaring supermassive black holes, changing Luke AGN, hopefully also the kind of events that Nadia mentioned earlier with the bound fluorescence, et cetera, et cetera. So this is going to be really starting in full swing over the next year when we commission the robotic fiber positioners in the south. So that's it. This is my summary. We're seeing many new samples, not just individual events, all of extreme variability events related to supermassive black hole accretion. These can be very insightful in terms of accretion physics, including super Eddington accretion, which I didn't have the time to mention, AGN unification, tidal disruption events. And again, you're going to hear more about this soon. Specifically, I showed you data from a change in Luke AGN caught in the act. We think we understand what's going on there in terms of, again, resolving the sequence. But still a lot of mysteries like the X-ray corona, which got destroyed and may be recreated. We don't know what initiated the event, which is a great mystery. And you're going to hear more about this from Tzvi Ran after the break. And again, we hope to see many more such exciting events and samples of such events and to understand their occurrence rates and links to black hole properties from surveys, including Sloan 5. That's it. Thank you.
Thank you very much. A lovely talk. Really, really interesting. Great that you've solved the problems. At least some of them, maybe.
Yes, some of them.
We have a question from Nikos. I'd ask, try and keep it brief and the answer brief too.
Thank you.
Yes, thank you. Very nice presentation. Very interesting work. I just wanted to ask you a basic question. So how do you suspect that the transient is indeed an AGN? Do you need spectra, or how do you know?
Right. So in all these events, let's go back to kind of the kind of data we have for this source. This source, there's no question about it. There was optical spectroscopy where you can do like strong narrow line ratios. Sorry, so it's a narrow line AGN. There was strong X-ray detection here with an X-ray spectrum that looks like nothing else but an AGN. The luminosity. All of that means it's an AGN. Other examples I showed were mostly, again, large surveys targeting previously known quasars. So there, of course, by definition, it's a quasar, but then if it changes look, it means it's switched off. Okay, so we're trying to combine, when we get new alerts, we try to dive into archival spectroscopy, archival all-sky radio, X-ray data, sometimes radio too, whatever we have. And if it used to be an AGN and it's doing some funky business, we're on it. And you saw some of the exciting results in Nadia's talk, and other things are going to be published soon too.
Thank you. And Michelle, if you've got a quick question.
Yes. You said at the beginning of your talk that it's difficult to obscure completely the broadline region. Now, so far I know the standard model, a CIFR2, is precisely an AGN where the complete broadline region is obscured by dust or something. So do you think your cases would challenge the standard model?
So, right. So to be clear, the kind of the classical picture is of this continuous reservoir of toroidal, reservoir of dusty gas, which obscures the central engine in type 2s. But, we're talking about things which change. So the explanation here is that this obscuring medium is actually patchy. It's made up of individual clouds. And this is, by the way, supported by a whole different line of study, and people have been resolving the torus for quite several years now. So you need something dynamical to change on time scales of months or years, in our case, even weeks, right? So if it is due to this thing, these have to be individual clouds. It cannot be the whole thing, doing crazy things within months. You can just do it from timescale arguments.
Yeah, okay. Yeah, I completely agree. I will talk about that a little bit in my talk tomorrow also. Yes.
Right. I should stress, though, I don't want to bring up a backup slide, although I have it. There are cases, there are some changes in AGN identified in the X-rays which seem to be doing exactly this. There is a cloud of dust going in or out of the line of sight. Sometimes we see both in and out. So this is exciting. It is possible. It's not impossible indeed.
Yeah. Thank you.
I'm going to call an end to this session and thank everyone, all the speakers this morning, for really excellent talks. So we have a break now, and we've jiggled the timetable a little bit. So we're going to break until Central European time will be 11:40. So that gives us 17 minutes to go and have a cup of tea, coffee, whatever you need to do. Come back, or it depends what time zone you're in, and come back refreshed and ready for the next part. So thank you, everyone, and we'll see you shortly. Wukash has put in the chat that there's a WonderMe link. So for those of you who want to go and hang out in the WonderMe, go there. And see you all in 17 minutes. Hi, Svi. You can start sharing the screen so we can see if we can see your slides. Can you hear me, Svi?
I hear you.
You're muted, Svi, at the moment.
Yeah, I can hear you very well.
Ah, good, and I can hear you perfectly.
And I tried sharing screen a minute ago and it seems to work.
Ah, perfect. That's great. There's still 5 minutes before we'll start.
No, sure, sure.
But I saw you there and I thought, okay, good. We have a speaker.
Yeah, yeah. No, I was sitting in on a PhD committee and then when it ended, I connected.
Okay.
So I heard the last talk, which was good.
Yeah.
Hello, Tzvi.
Hi, how are you?
Fine, how are you? Thanks for joining us here.
Well, thank you for inviting me. It was
Have you been in the Wonder Me, Łukasz?
Well, there's not much going on there. Some people are clustering and talking, which is the intention. But well, I was hoping for more traffic there, more people joining there. Maybe there is no time.
it's
by the
difficult.
time yeah, it's hard. You're in your home, or at least I'm in my home, and I need to make the coffee, and I have to go to the bathroom.
Yeah.
And by the time you've done that, there's not much time.
This is the part which is most difficult in this virtual interaction, the personal one-to-one. The talks go fine on the Zoom, but then the exchange afterwards is difficult.
Exactly. Yeah, we'll definitely miss this.
Yeah, the only way I managed to do it, and it sometimes works, but not always, is to send a message to individual person and ask him, can we chat later, and so on, and then it works.
Yeah. Well, that's good. Tzvi, would you mind sharing your slides now?
Yeah, sure.
Fantastic. Yeah, that's good. That's nice and bright. People will start drifting in. I guess we have to give, I don't know how you tell if everybody's in the room or not. So we'll give people.
One other feature, one other sociological feature of Zoom is that there is a few minute time delay. People are usually more slower coming to the room in Zoom than otherwise. I don't know why, but that's how it is.
But we stream everything, so people can rewind and catch up on YouTube if they missed something important. So I think we can start, Simon.
Have we started streaming already, Łukasz?
Yeah, we've been streaming through the break as well.
Yeah, oh, great. I'm happy about that. Okay, Zvi, I'll invite you to start. I will give you a warning after 10 minutes are elapsed, so you know there are 5 minutes left, and it would be good if you can wrap up after that in 2 minutes or so we have time for questions.
Okay.
Thank you very much.
Okay, good afternoon. It is still morning here, but good afternoon to you elsewhere. And I want to thank the organizer for inviting me to talk about this exciting topic, titled Disruption Events in AGN. And the way I describe it, it's a phenomenon in search of observations. We might have seen some events like this. We certainly have seen, but we are not sure that we identified them. And this work is done in collaboration with Edwin Chio Chan here in Jerusalem and with Julian Krolik at the Johns Hopkins. It was published in 2 update papers and a third one on the archive. And unlike the other talks here, it's mostly a theoretical work. But the reason that I'm very excited in giving this talk here is that it is theoretical work, but in search of observations. We are looking for observations that will identify, and this is you're just the right community that can provide us with these observations. So we already heard from Yair and others about the regular TDE, and this is a famous picture from Martin Rees from 88, in which a star comes to the vicinity of a black hole, it's getting disrupted, and it is ejected, and then some of the matter comes back to the vicinity of the black hole, and the accretion goes on, and the other processes goes on, and so on. So this is a regular tidal disruption event. But here, we want to realize that about few percent of central black holes, central galactic black holes are active and have an accretion disk. And the accretion disk is large compared to the scale involved. And then this whole, when we try to estimate what happens in the process, we have to take account of the interaction of the stellar material with the disk. So how does it work? First of all, there is the first passage, or the zeroth order passage. The star comes, and it is being disrupted by the black hole. At this phase, the density of the star is so much larger than the density of the disk that it passed basically unperturbed. And if it was far from the black hole, then nothing would have happened to the star, nothing would have happened to the accretion disk, and it would just go through. But if it is near enough to the black hole, the gravitational field of the black hole disrupts the star, and we have a regular tidal disruption event, and we have the star is now going out and being tidally deformed, and it is getting out of the system. So the first passage, the disruption event, goes basically the same as if it was in vacuum, but the story becomes very interesting. T-naught later, T-naught is the time that takes for the boundmost material to come back to the vicinity of the black hole. It is of order of about 1 month for typical parameters. Then we have a much thinner stellar stream characterized by the subscript S. And the stellar stream now hit the disk. And now the densities are comparable, or at least not so different. And we faced a very interesting interaction. And the interaction is between the stream of the disk, which is here more is the important stream is the angular stream, the stream surrounding, going around the black hole, and the stream of the that is coming and interacting with it from the outside, from the stellar debris. How does this look? Before we have to think about this ratio. This ratio is typically slightly larger than 1. It depends strongly on the unperturbed disk parameters, and these unperturbed disk parameters will depend on the luminosity of the disk. So depending on the luminosity of the disk, this ratio may range from slightly less than 1 to significantly larger than 1, where the typical parameter, the stream, is about 4 to 10 times larger than the disk stream. So these are typical parameters. How does it look? This is a movie that shows 3 slices of this. You can see here in the top left the stream hitting the disk, and you can see it also on the bottom. And this is on the right here, you see a top view. And the most prominent feature that you see in the top view, this is, by the way, density. And these simulations last for about 12 days. And the most prominent feature that you see here is the inner region of the stream, of the disk, is very quickly evacuated from matter. Matter goes very quickly from this region, falling onto the black hole. And there's also the spiral structure, the spiral waves that go out into the outer part of the disk and perturb it. So you see here the stream is here hitting the disk. It is getting through the disk, and it is evacuating the inner region of the disk. And the big, so we understand hydrodynamics fairly well. The big question is how does the what is the corresponding observational signal? And this is still a partly open question. What we know is that there is a hyper-Eddington flux onto the black hole. The central region of the black hole, of the disk, which is contain a fraction of a solar mass, falls onto the black hole on a time scale of of about a day or so. This is the time scale here of how fast is the inner stream falling. This depends on the mass on the stream ratios, but typical values is few orbital timescales. The matter falls onto the black hole, and this gives us hyper-Eddington flux in terms of mass onto the black hole. Now, translating this to luminosity is more complicated, and the problem is that while the energy dissipation rate is much larger than Eddington, we see here on the top left the Eddington ratio, the energy dissipation ratio in terms of Eddington, and you can see that it goes in extreme cases up to more than 10 Eddington, maybe even reaching 100 Eddington in extreme cases. But the cooling time, the system there is very thick and dense, and the cooling time is such that most of this energy that is dissipated simply goes with the flux into the black hole, falls into the black hole. And more or less we have this balance that what you get out is roughly Eddington luminosity, actually slightly less than Eddington. But you can see here in the figure on the top right, we have about half Eddington luminosity, and this is more or less, there is more or less a plateau of this luminosity lasting for about 10 days or 20 days, and then there is a decline following this region. The problem is that this is the result of the hydrodynamic simulations. I must say that because of the complicated radiation transfer, which we could not solve, it's a doable numerical problem, but extremely cost-effective ones in terms of the combined hydro radiation computation. So we haven't computed it yet. My guess is that this will come as in the UV, but this is just a guess. So in spite of the insistence of the referee of this paper, we insist not trying to give a spectrum because we don't really know exactly the spectral shape of this radiation, but we expect it to be in the UV, this regime. But we also expect another expectation that happens here is that the inner region is destroyed. And when the inner region is destroyed, this means that this may lead to a destruction of the corona, and it may lead, in this case, to effect like the one that we heard in the previous talk by Benny, in which the X-ray, the hard X-ray disappears for a while because of the effect of the destruction of the inner disk, and the complete evolution of the luminosity is even more complicated because of the complicated structure of clouds and other material that surrounds the system, and reflection and so on that we heard in the previous talk. So the full prediction of how this, the full prediction of how this will look is still not obvious. There is another component, which is the outgoing matter, and because the matter goes through the disk, and this matter hits the disk, and when it hits the disk, there is now a second component here of soft gamma rays with energies of few hundred keV, also lasting for about a week. This is from the interaction of the disk or of the stream with the farther part of the disk. One final remark. If we go back to Yair's talk, and we mentioned here talk for a second about regular TDE, then the question is how the energy is dissipated. One model, the most common model, is a disk, which is reprocessed, radiation is reprocessed. A second model, which is outer shocks, in which the matter self-interacts with itself and produces emission at around 10 to the 15 centimeter from the center. This is my favorite model. As a footnote, I would say that with Tetsuya Matsumoto, we have recently pointed at some problem with this model of the accretion disk, but this is a second issue. What is important for here is that if we put an accretion disk here, that this will disrupt both models, either the outer shock model or the accretion disk model, will not work as they are originally proposed. So in both cases, we have to rethink not only also about where the optical emission is coming. It is not the same old process that we have seen in regular TDEs. So this is the results. Let me summarize them. Initially, the kinetic energy is dissipated. Then the stream penetrates the disk. A significant fraction of the inner disk, which is of order of the solar mass, falls very quickly onto the black hole. And this emits Eddington luminosity, most likely in the UV. Rest of the disk is heated, becomes much thicker. And for a few months, we'll see how the disk is recovering from this effect. Then there is a flare, as I mentioned, probably most in the UV. There is a plateau and it's going down. And this is what we have to look for. This is what I'm asking you to look for some activity like this in AGN, and hopefully we can search for it. So the summary is that these TDEs are very different from regular TDEs, and it is a new exciting field of observation, both observations and theory. Observations because we have to identify this event, and theory is because we have to identify these events. We don't have yet the full theory on how this event will look. And there is an additional interesting statistical question, which I haven't discussed here, is what is the fraction of AGN variability that can be explained as TDEs in AGN. Maybe this is a driving force for the activity, or at least for a subfamily of the activity. So I think I'm on time. And I'll stop here. Thank you very much.
Perfectly on time. Thank you very much. I think that's a question in the chat. Would you like to ask it, Marzena? Or I can read it if not.
No, I can ask. So hi, it's a very, very nice work. I looked through this paper actually, and it looks really, really interesting to me. So what I want to ask is what are actually these physical parameters which you use to describe this accretion disk?
Oh, thank you for the question. For simplicity, we assume that the disk is described by Sakurai-Tsunaev, just a Sakurai-Tsunaev disk. And in this case, we assume that the disk is characterized by one parameter, which is the total luminosity. And if you take a standard Sakurai-Tsunaev disk and you assume alpha is 0.1, then by specifying the black hole mass and the total luminosity, then you know the disk parameters. Of course, life can be much more complicated if disks are more complicated than Sakurai-Tsunaev disks, which they probably are. So there is a lot of things to do here with this idea. If you take another type of disk, the story will be, the details will be different. I don't think that the parameters will be very different. For example, I will give you one example. In these simulations, we assume that the stream is coming perpendicular to the disk. This was just because this was a simple thing to simulate. We recently simulated various angles in which the stream was coming from different directions. The results are more or less the same. The inner region is destroyed, adding to luminosity coming out in some, probably in the UV, but maybe somewhere else.
Okay, thank you.
Definitely non-thermal.
Okay.
Zvi, could I ask you to stop sharing screen? And at the same time, Siegfried can ask a question while the next speaker, Nicholas, starts sharing screen, please.
Can you have the TDE resulting from?
Oh, I put my question in the chat already.
Yes, I see.
Yeah.
So I'll read the question. Can you have a TDE event from a compact star like a white dwarf hitting the disk? If you have a compact star, it will be much more difficult to disrupt it. So just the passage of a compact star in the disk will not disturb the disk at all. It will just go through the disk and so on. To disrupt a white dwarf, you have a much more compact black hole. So this is not, you are now not talking about a regular AGN. We are talking about something like large intermediate mass black hole, something of 10 to the 4 solar masses or something like this, with a disk around it. I'm not familiar. I'm not sure that such systems are that common.
Okay, thank you very much. I'm afraid we have to move on to the next speaker now. So Nikos, if you'd like to begin, I'll give you a warning when you've had 10 minutes.
Okay, can you see my screen and mouse?
Yes, and your mouse both.
Perfect. So
we hear you.
Hello, everybody. I'm Nikos Mandarakas. I'm a PhD student in the University of Crete in Greece and working at the Institute of Astrophysics, where we do a lot of interesting stuff, but we really love polarimetry. And this is what I'm going to talk to you about today. So how we can use polarimetry as a tool to search for AGN counterparts of unidentified Fermi-Lat gamma ray sources. First of all, a few words about the Fermi Gamma Ray Telescope. So it operates since 2008 in the gamma ray range and has produced more than 5,700 gamma ray sources. The latest release was in 2020, but we did this work before, so we used the previous data release, which contained a little more than 3,000 gamma ray sources. So the problem with gamma ray sources is the poor localization. So as you can see in your top left plot there is a gamma ray source with its 1, 2, and 3 sigma confidence error ellipses, but it is obvious that it spans across several arc minutes in the sky. And a similar image in the optical, as you can see in the bottom, has maybe hundreds of sources. And it is often very challenging to find the true counterpart of the gamma ray radiation. Now, it makes sense to look for AGN counterparts for gamma ray sources because the vast majority of the identified Fermi sources are actually AGN. So you can see in your right a sky map with all different classes of classifications, and with blue are the AGN. So they completely dominate the identified sources, and particularly 85% of them are blazars. Now, AGNs are, and particularly blazars, of course, are naturally polarized because of the synchrotron emission that can arise in the relativistic jet. But even in the case where there is no jet in radio-quiet quasars, we can have a polarization due to scattering by the dusty torus that surrounds the black hole. Unfortunately, AGNs are not the only object that can seem polarized in the sky. So, for example, sources that lie behind the interstellar medium can seem partially polarized due to the magnetic fields that trace the interstellar medium. So magnetic fields align the dust within the clouds, preferentially in the, perpendicular to the magnetic field, and thus dust grains attenuate radiation preferentially along their major axis, and therefore the background sources look polarized with a polarization angle similar to the projected magnetic field direction. So on your right, you can see the Polaris flare region, a work by Gina Panopoulou and collaborators. And the red lines represent the polarization degree and the polarization angle of the background sources. So from this plot here, it is obvious that there is a trend. There is a distinct pattern that can actually hinder any AGNs or any other naturally polarized sources that lie on the same region. So now, before I go on, I'd like to introduce you to the instrument we used, which is a RoboPol, robotic polarimeter, which is mounted in the Skinekas 1.3 meter telescope. And it has the advantage that it is a 4-channel polarimeter. That means that it splits the incoming ray into 4, and we can simultaneously measure Q and U Stokes parameters with a single exposure. So it makes it very fast in comparison to traditional polarimeters. And RoboPol's job was primarily to monitor gamma-allowed blazars. And through this RoboPol program, we know that gamma-allowed blazars are highly polarized, 5% or more even. Now, as I said, there's the problem of the interstellar medium, and this is because we wanted to evaluate the detection efficiency before we test our method. So we used information from the Polaris flare cloud in order to simulate the field. And we used information from the RoboPol sample that I just described to simulate an AGN that can lie in this region as well. We carried the simulations, and we wanted to see how many times we could detect actually such a blazar with 3 sigma or 5 sigma precision. And the results are shown in your bottom plot, where in the x-axis you can see the average polarization of the field, and the y-axis is the detectability fraction of these AGNs. So it follows from this plot here that for example, in high galactic latitudes where we expect an average polarization of 1% or even less, we expect to have detection efficiency of around 80%. And moreover, we used the polarization data of polarized stars by Halley's and the reddening data from Schlafly in order to find the correlation between reddening and polarization. We applied this to the unidentified Fermi sources, and we calculated that in the case of the third Fermi gamma ray catalog, we would be able to detect more than 500 AGN using this method. So I will present you now some results. We observed 4 different Fermi fields, and in one of them we got lucky and we found such an outstanding source. So this is the field that we studied, that I showed before as well, along with the 1, 2, and 3 sigma error ellipses. And as you can see, there are many sources that can be seen in the optical. And therefore, we measured the polarization of most of them, and we made this nice plot. So on your left, you can see the Q and U Stokes parameters for all the sources in the field. And there is clearly one outlier. So this mark here with, it is marked here with red, and it clearly deviates from the average trend, right? And you can see the same picture on your right, where you can see a histogram of the polarization degree of all the sources in the field. And again, the same source is clearly away from the others with a polarization degree of 5.2%, while the average polarization of the field is 0.91%. Now, here's the field that we studied, as I showed, together with the error ellipses. And you can see our candidate, which is this little spot here, lies just outside the 2 sigma confidence error ellipse. But this is for the third data release of Fermi. And I said now there is the 4th data release, which has twice as much exposure time and a number of analysis improvements. And for example, the 4th data release has provided updated position and better localization for this gamma ray source. And this is the new gamma ray position. And as you can see with red here, our candidate lies within the 1 sigma confidence error ellipse. So I'd like to draw your attention here to the fact that it is very extraordinary that polarimetry was so precise even before Fermi updated their pipelines and could better localize the gamma ray source. So finally, what is left is to confirm the AGN nature of our candidate. And for this reason, we took spectra from the Skinekas Observatory. You can see, as you can see in the top left, we found that our candidate is redshifted. You can see emission lines here. And also we gathered archival data from optical infrared, UV, and X-ray emissions. And we plot them together with the gamma ray data from the Fermi for this field. And we also found the position of our candidate in the BPT diagram, which is on the bottom.
10 minutes, Nikos.
Yes, thank you. Our candidate is depicted with a yellow star here. So these diagrams are diagnostics for galaxies. And our candidate is very close to the star-forming plus AGN region. So based on all these results, we argue that this candidate is probably a hybrid source, a star-forming galaxy with an obscured AGN at its center, for example. So why is this important? Now, this research becomes very relevant with the coming of Pacify, which is the largest optopolarimetric survey, and it is going to see first light this summer, and it is going to survey millions of stars across the sky. Now, in this plot, I'm showing with blue points all the unidentified gamma ray sources of the fourth data release of Fermi, and with the shaded red region is approximately the area that will be covered by PACIFI. So we'll have the opportunity to mine the PACIFI data and basically search for hundreds of AGN candidates as counterparts for gamma rays. And this is basically for free because the data will exist and we can easily do this work. So finally, what I'd like you to gather from this presentation as a keep-home message is that polarimetry is a very powerful and reliable and very fast tool for detecting AGN, fast compared, for example, to spectroscopy, and it can be extremely useful in this big data era. And it can be useful not only for Fermi, but also, for example, for Gaia alerts. Having information on the polarization by PACIFI, when an alert comes up, polarimetric information can be included, and potentially someone could check whether the alert, whether an AGN is responsible for the alert. And it was very fortunate that Benny talked earlier about changing look AGNs, and I think this is a very precise example of how polarimetry, in this case, would add this bit of extra information that we would need to confirm that a source is actually an AGN. Thank you very much for your attention, and if you want to learn more on this work or contact me, this is the time for you to take a screenshot, and thank you very much for your attention.
Thank you very much, Nikos. Do we have any questions? I'd like to ask just a very quick question. I didn't understand exactly the specifications of PACIFI. Can you, well, I should screenshot and go and look at it. But what is the,
sorry,
is it spectroscopic?
The diagnostic diagrams?
No, your instrument, if I've understood.
So the instrument, Robopol.
I thought PACIFI was the next generation. Or...
Yes. Yes. So
yes.
we did this work with Robopol instrument.
Yeah.
But PACIFI, so Robopol is optimized for single target.
Yeah.
But PACIFI will be a wide field survey, and
right.
This is why it will give the opportunity to do so good science.
Right, right, and why you get the multi-object coverage.
Right, exactly.
Okay, okay, thank you very much for that. Then I think we'll move on now. Thank you very much. If you could stop screen sharing, and if Benito could start screen sharing.
Yeah.
I see you, Benito.
Okay, can you hear me and see the screen?
You see the slide, we hear you fine.
Okay.
I will give you a warning after 10 minutes, Benito.
Okay, perfect. Okay, first I will like to thank the organizer for let me give this talk. I'm Benito Marcote. I'm one of the support scientists of the European VLBI network. So that means that I'm kind of an outsider here. I'm just fully a radio astronomer, and I've only taught optical data a handful of times. But I work in transient events, and actually we have close ties with optical alerts that we follow up later on at radio frequencies. So actually in this talk, I want to give just a short and quick summary of some of the user cases where that collaboration following optical alerts conducts to really nice research cases, yeah, using radio follow-ups. So I'm not going to discuss about radio astronomy in general. I will focus on very long baseline interferometry, VLBI, which is the ones providing high resolution. And this is especially critical for transient events because we can reach resolutions that allow us to study the morphological changes and how these events change on scales of, let's say, astronomical unit for typical galactic events, or on the scales of parsecs to redshifts of up to 1. So we can already explore the morphological changes and what happened in these systems within months and year time scales, and we can resolve these systems. So this has been proven to be really successful, especially in the last years with a lot of a variety of new events like gravitational waves, on longer time scales, gamma ray bursts, supernovae, novae, several X-ray binaries, yen. So we have a huge variety of events where we've been following up and then producing some nice science there. And one thing that is common in most of these transient events is that in most of the cases, we've been following up the optical localizations or the optical triggers. And only after that is when we conduct our radio following up. So concerning VLBI, I will focus on the European VLBI network that is currently the most sensitive VLBI network at centimeter wavelengths, and this is one of is the observatory that we run. So it actually uses a vague idea of European because whereas most of the antennas that we are using are in Europe, this is the core of the array. We are also using antennas from Africa, Asia, America. So basically this is a global network. And this is why it allows us to reach the millisecond resolution that we can achieve in these observations. So we basically combine the data from a large number of antennas all over the world. And of course, we need a place to do that. That's Gaia, my home institute, located in the Netherlands. And here is where we combine and process all the data from all the antennas. And actually, just recently, we are moving to be a partner of the Joint Optical and RadioNet pilot project. So we are actually really interested on strengthen the links and the collaborations between the optical and the radio community. And from our part, we try to involve the AVN more on this following up from the Gaia alerts. So actually, if you look into how the AVN runs, you could first think that this is not an observatory suitable for transient observations because we are not observing all the time. We only have, let's say, 3 of around 20-day regular sessions per year with a tight schedule. And then we only have 40-hour runs that are conducted once per month. So we are not observing all the time. So in principle, for transient events, this is not what you want. But actually, if you look at the publications that appear from using EVN data, and I didn't have more up-to-date plot, sorry, but you see that basically 1/4 of all the publications are related with transient events. So it's clear that everyone can use this observatory to observe transient events. And well, in any case, I didn't say, but we can trigger basically one within 1 day, so that's also possible. But the feasibility of using the EVN for transient events emerged from basically the nature of the radio emission. This is basically common to most of the transient events, independently on their nature. We know that the radio emission evolved on a much longer time scales and much slower than what happens in the optical regime. So that allows us to first wait until there are some optical alerts, the position of the events has been reported, and then start conducting observations weeks and months after the events. A clear case for that was the first neutron star binary merger that happened in 2017, whereas all the fun started within seconds and hours, and there is where most of the observations were conducted, and most of the optical emission were reported within our days. The radio emission only appeared 16 days after the event. So we just needed to wait a long time, almost when everyone else were slowing down, and we started our observations. And actually the radio emission only peaked at basically half a year after the event. So it's when we had our more valuable data. And actually we conduct observations in this case just by studying the afterglow, the radio afterglow that appeared after the merger. And actually, even when all the optical X-ray studies were already taken into place and reported, there were still some questions that were only resolved thanks to these radio observations. In particular, they were still not completely understood if the afterglow, or the material that escaped from the system, it was a jet that managed to cross the kilonova and propagate into space, on or off if this jet basically choked into the kilonova and then it had produced a more spherical expansion, the so-called cocoon. So to resolve this question, it was only possible thanks to these radio observations with this resolution, because in that case, we are at the level that we could resolve the emission and this structure, and then we could distinguish which of the models were happening there. So there were two teams. One observed the actual relativistic proper motion of this afterglow, and we also put constraints on the size. So we saw that they were compact enough to be explained by the successful jet, that they were just propagated away from the system. And that was feasible because we compared with simulated images, assuming the different possible models. So this was one of the first cases we did this kind of studies. Basically, we are also applying the same phenomenology to other similar kind of systems where you have an afterglow escaping from the system. So this was a kind of particular and extreme case given the time scales involved. This was a long gamma ray burst where phenomenologically you have something similar. You have first kilonova, the burst, and then the radio emission only comes after the bulk afterglow. So much longer time scales. And actually this was not a long yearly discovered by the gamma ray emission or even the kilonova. It was discovered as a truly radio transient event with a light curve that has been decaying for the last 30 years. And what was interesting is that the light curve resembled the ones expected from long gamma ray burst afterglows. But of course, after 30 years ago, we didn't have any gamma ray emission, gamma ray observations there. So by studying the size of this afterglow at this time, just last year, we managed to put constraints on the size of the emission, which, assuming the age of the system, we managed to put constraints on the average. Yeah, okay. On the average expansion from this system to be midly relativistic. So actually we found that this is a completely afterglow consistent with a long GRB one where the actual GRB was not observed. So this was the first studies that we did, and now we are following actual long GRBs reported in the gamma ray and optical community, and then we try to make more detailed studies of the afterglows. So we can see what happens with the jet and the dependencies of that with the interstellar medium. And if in all cases you always have a jet that can choke with the kilonova, what happens if that depends on the density that you have in the surrounding medium, on things like that. And of course, these are just a few samples. In the past, there has been really nice studies of supernovae in our galaxy, where you can trace how the material propagates into space within just a few months. Or the first tidal diffraction event that was studied in detail, where they observe what happens after the event. So all the material that propagates into space starts emitting radio, and you see its motion afterwards. So this has been just a sample, and I will finish with one that is one of my main topics, which is fast radio bursts. Maybe a few of you have heard about that. It's a quite new population of transient events because they were discovered just a bit more than 10 years ago. And these are flashes of radio waves for now that only last for a few milliseconds. We still have no idea what's the true nature of these events, and we've only localized a few of them. And I saw here only the 2 of them that has been localized to millisecond resolution, so we know the host galaxies and the local environments. In these cases, they are associated with or close to star-forming regions, but we know that this is not true for the whole population. So far, they've only been detected at radio wavelengths, but they are models predicting optical emission. And recently has been a galactic case where these FRBs were detected at the same time as X-ray flares. And actually, we are thinking that if that happened in a known magnetar, then it may happen in systems where you have binary systems, when you have a magnetar, and actually following the X-ray and basically the optical triggers that typically report when these activity periods are produced or are happening, can allow us to trigger new radio observations there to try to search for FRBs. Because again, in this kind of systems, we have no idea still about what's the nature, and we expect that maybe FRBs can be produced in different types of systems. And then I will just end up here. The summary is that we know that VLBI observations are a really unique following up of optical transients that allow us to trace the morphological changes on months, year time scales. So we've been in the past following up these Gaia alerts and in general optical triggers, and we are really want to strengthen up this collaboration because this is basically motivation. We have really high resolution, but we need an a priori localization there. And that's it from my side.
Thank you very much, Benito. It's a very bright future, I think, here.
Thanks.
Do we have any questions? We've got time for a quick question if there is one. Can I ask you, Benito, to stop sharing screen now? And Dimitri can begin sharing screen. And okay, I think we'll move on to Dimitri's talk now, please. Dimitri, we see your slide.
Okay, can you hear me?
It's a bit distorted. Can you say something again?
1 second. I will try to.
Better. That's
okay, perfect.
That's better.
Hello, everyone. Okay. Hi, everyone. My name is Dmitry Blinov. I'm a postdoc at the Institute of Astrophysics of FORF in Crete. And I will try to explain you why we recently started measuring optical polarization of AGN from Gaia alerts. So it started soon after the data release from Gaia. My collaborators in this work, they cross-matched radio catalog of AGN positions with Gaia data. And they discovered that the offsets between radio and optical positions of AGN, they are systematically aligned with jets in this AGN. So what I'm talking about is demonstrated here. And these are 4 different AGN. These are VLBI maps. And these little black ellipses, they demonstrate their radio positions. They, in most of the cases, they coincide very accurately with so-called radio core. And there are also other ellipses here showing the optical photocenter position according to the Gaia data. And if you plot the distribution of this angle psi between the jet direction vector and the VLBI to Gaia vector, you will see that this psi angle tends to be distributed around 0 and around 180. So this means that the optical photocenters
tend to be shifted from the radio core down the jet, like in this case, or in the opposite direction, upstream the jet, like in this one. So the interpretation of this thing proposed by these authors in the works I'm citing here was that in the downstream case, we observe in the optical an extended optical jet emission, while in the upstream case, we observe the central engine emission, the accretion disk, and the broadline region emission that shifts the optical photocenter from the VLBI radio core towards the black hole upstream the jet. Last year, we published this letter in MNRAS, where we collected optical polarization measurements for several hundreds of AGN. And we demonstrated that these sources with VLBI to Gaia offsets downstream the jet, we tend to have higher optical polarization compared to the sources with upstream offsets. So here are the median values of optical polarization. And this finding perfectly fits with this model that I explained before, because in the downstream case, we observe the optically thin synchrotron emission of a jet, and it is known that the synchrotron emission is intrinsically highly polarized. While in the upstream case, we observe the central engine emission from the accretion disk and from broadline region, and the polarization here is produced by scattering. And it is known that scattering is not so efficient polarizogenic mechanism compared to synchrotron. And moreover, we know that we observe here our line of sight is close to the jet axis, so we see this system in a very almost symmetric way. So this also cancels out, introduces extra depolarization. That's why the polarization of these sources in the optical is lower. So we find this very interesting, and we believe we can learn a lot of new about these disks and jets in AGN using these VLBI to Gaia offsets and optical polarization, but this is only the beginning. So we started last year an optical polarimetric survey of these kind of sources with significant VLBI to Gaia offsets, and we so far managed to observe around 100 of new AGN using these different instruments. We also hope that, as Nikos mentioned, this survey that will start this year, this summer, called Pacify, that it will deliver for free hundreds of AGN measured in optical polarization. But what I find more important is to start monitoring of AGN and optical polarization simultaneously with Gaia, because we know that Gaia revisits every source on the sky approximately every 26 days, and we know that this time series data will be available in the future. So we expect to see the variability of this VLBI to Gaia offsets. We expect to see the jitter of the optical position depending on the events happening in the jet or in the disk. But unfortunately, we know that monitoring is very expensive in the sense of human power and observing time. So instead of performing monitoring, we can go for a cherry picking by following up Gaia alerts in polarization. So we know that there is a Gaia alert about a flare in AGN released approximately every 16 days. And also I found that there have been so far 54 alerts about this kind of AGN I was talking about before, with significant AGN with significant VLBI to Gaia offsets. So we find it very important to follow up these alerts in optical polarization, because we can learn a lot of new about the disk and jet system and separate these two things in the optical emission. And we can solve a number of different problems related to AGN physics. And here I demonstrate one of such problems. This is so-called orphan flares. So here we see an optical flare in one of the blazars, which is rather high in amplitude. It's almost 2 magnitudes, but at the same time, we don't see anything in the gamma rays. So the source is very close to the lowest state in the gamma rays. There are 2 alternative hypotheses explaining how these kind of flares can be produced, and they are very much different in physics. One of them says that...
Can you start wrapping up, please, Benito?
Yes. Okay, I will end up here. I will just say quickly that having enhanced astrometry information from Gaia and polarization information, we could easily, immediately distinguish between these 2 models and choose and see which one actually takes place in nature. So I had some other examples, but I will skip them, and I will leave you with my summary slide. Thank you for your
Thank you very much. Do we have a quick question? If you wouldn't mind stopping sharing now, Benito, so that Yaroslav can start sharing. I have a very quick question. If we were able to release epoch photometry, astrometry during the Gaia transients, during the events ongoing, would that be of use? Because the really precise astrometry won't come until many years away, the epoch astrometry. But at the 10th of an arc-second level, would it be useful?
I think it would be extremely useful for this kind of work where we want to see if the photocenter position changes in each of these kind of events. So we would see if the photometric position already started changing, we would follow up this kind of event. If it's not, if accuracy is not enough, we could go to another event.
Okay. Okay, I'm going to ask you a question offline about that. Thank you very much. Yaroslav, can we test your voice?
Yes, can you hear me?
Yes, we can hear you fine, and we see your slides. I will give you a warning after 10 minutes. Please go ahead.
Perfect. Thank you. So, hello everyone. My name is Jaroslav Merc. I am a PhD student at the Astronomical Institute of Charles University in Prague, in Czech Republic, and at the same time at the Institute of Physics of Pavel Josef Šafarik University in Košice, Slovakia. And I'm pleased to talk here about first symbiotic star discovered by Gaia, which is a work done in collaboration with many of you. So several of you will probably hear nothing much new about this, as you co-authored the paper. But still, I think this is an interesting opportunity to talk about a nice outcome of Gaia mission and Gaia Science Alert as well. So at the beginning, I would like to just very quickly introduce symbiotic stars, as probably some of you are familiar with this class of objects, but not everyone. And then I will talk about Gaia 18A which is the object which we studied in details. So very quick introduction, one slide introduction to symbiotic binaries. These are strongly interacting binaries, which are among the widest interacting systems we know. These stars are open binaries, and typical orbital periods of these systems are hundreds of days for most of the stars, but we know also the systems with orbital periods of tens of years. And the most typical symbiotic binary, but there are many different kinds of them, but most typical one consists of a cool giant and a hot compact star, which is mostly a white dwarf. I put it here a very simple model of a symbiotic binary with a cool giant with a strong stellar wind, white dwarf, which is accreting the matter. The whole system is usually hidden in a circumbinary envelope. And usually the mass transfer between the system, between the components of the system is via the stellar wind. In some cases, it could be thanks to Roche-Loeb overflow. Why symbiotics are important and interesting? It's because these stars are unique astrophysical laboratories in studies of stellar interaction, mass transfer and accretion processes, in study of stellar winds and their collision, in study of formation and collimation of dust formation and destruction, in the study of outbursts, of course. And also these systems are important in study of stellar evolution, not only in the study of evolution of binary stars, but also symbiotic binaries were proposed to be a possible or one of the possible progenitors of supernova 1A, which we know is important class of objects. So now to Gaia 18A EN. This brightening of this object was detected by Gaia at the beginning of 2018 in January, and it was announced by the Gaia Science Alert on January 17th. In the alert itself, it was referred to the star as a bright emission line star in galactic plane, which brightened by 1 magnitude, because the star was previously classified as an emission line star. Soon a spectrum was obtained as in astronomer's telegram based on a spectrum obtained by X-Shooter instrument on VLT. The target was classified as a nova with a question mark. We collected the observational data, available observational data on this target, especially low resolution spectroscopic observation using the Liverpool telescope and before mentioned medium resolution spectrum from X-Shooter instrument, and also photometry from Gaia and the follow-up network with several telescopes and as this was mentioned one of the previous days, these follow-up observations were calibrated using the Cambridge Photometric Calibration Server. And also we supplemented this with observations from Assassin, Ogle survey, Atlas survey, and Bochum survey of the Southern Galactic Disk, especially to cover not only the outburst stage or this active stage of the object, but also the previous questions, as you will see a bit later. So what we have found is that the spectra which were obtained for this object satisfy the conditions for the symbiotic classification. Especially, we can see a presence of a late type giant in the spectrum, and in addition to that, we can see emission lines of ions with a rather high ionization potential of at least 35 electron volts. That's the classification criterion or definition, but we can see rather highly ionized species of iron, or for example, in outside of outbursts, we can see also emission lines of Raman scattered oxygen lines, which is here. It's not very well seen in this scale, but definitely the line is here, and this line is exclusively seen only in symbiotic binaries, so it's enough to see this line in an object to classify it as a symbiotic binary. So we have these two spectra for this star. One was obtained just a few days after the maximum, and the second one is later. As you will see here in the light curve. So basically, this is just a zoomed part of the light curve where you see the first outburst. But as you see, there is a series of several outbursts, and the arrows here mark the positions or the times when the spectra were obtained. So we have one during this first brightening, and the one in between the first brightening and rebrightenings which were observed. So basically what you can see here is a series of outbursts which were observed in 2018 of 0.5 magnitude up to 3.3 magnitudes, this first one. And the amplitude, what we see here, and the duration of the outbursts basically resemble the behavior of typical classical symbiotic stars. As for example, it's Aged Draconis or Andromeda, a prototype of this class of objects. We have also studied the available data from the time before this active stage of these systems since 2010, but no brightenings were detected in that period of time. And actually now the system is again in quiescence, so we don't see any brightenings or outbursts after this series of events in 2018. We also used the quiescent light curves to try to search for any periodic variations, and basically what we have seen is that there are several minima, and we tentatively tried to obtain the orbital period of this system, which is around like 487 days. You can see a large scatter, of course, in the light curve because of several reasons. But what you can also see that there is maybe some evidence of a secondary minimum at the phase 0.5, which could mean that the giant might be filling or almost filling the rho slope. I will say something about it on the next slide. And the reason for the large scatter may be due to the short-term variations on the timescale of 50 to 200 days, which is somehow typical for symbiotic binaries, because the cool components in symbiotic binaries often pulsate with such periods. So that might be the reason for the scatter in the light curve. But still, some like long-term monitoring is needed to confirm the orbital period of the system. So on almost the last slide, I would like to talk about the cool giant, because it's quite interesting in this system. We have used the VLT extruder spectrum of the system to derive atmospheric parameters of the cool giant. And basically what we have found is that this is somehow typical symbiotic giant of a spectral type M, which is the most typical in symbiotic stars. There is a small group of yellow symbiotic stars with K or even G giants, but most of them are M giants with effective temperature around 3,500 kelvins of a slightly supersolar metallicity. But what is interesting is that for a distance which we have inferred for the system, the radius of the giant is quite large. Therefore, this somehow is, or we can tell based on this that the giant might fill its rho slope. But the most interesting is its luminosity, which is rather high for symbiotic giants, and it makes this symbiotic giants in Gaia 18 AEN one of the brightest symbiotic giants. So the system is quite interesting. So just to conclude, I think I am quite well with time. Gaia 18 AEN experienced an outburst of 3.3 magnitude in 2018, followed by several rebrightenings. The outburst was accompanied by changes in emission spectral lines, which is typical for classical symbiotic stars. The cool component of the system is an M giant, one of the brightest symbiotic giants we have observed. The near-infrared spectrum and also infrared photometry from TUMAS and WISE satellite is consistent with non-dusty S-type symbiotic system, which is this more numerous group of symbiotic systems. So the general conclusion is that Gaia 18 AEN is the first classical symbiotic star discovered by Gaia satellite. So thank you for your attention.
Thank you and congratulations on very, very, very nice work. And I was just looking at our webpage and I realized we haven't updated the classification, which is something I will do immediately.
Perfect.
That's great work. We have time for a question or two if there are any questions. Maybe you can stop sharing now and so we can get Michal ready. So there's a question from Milena. Milena, go ahead.
Hi, Jaroslav. Thank you very much. Could you comment a bit on if when you derive spectroscopic parameters of the red giant star, have you used only the red part of the extruder spectra, or you also use the other parts of it?
Yeah, no. We have used only the red part because the reason for that is simple. Basically, in whole optical part of the symbiotic spectrum, there is a mix of radiation from the giant, from the hot component, not in quiescence, but in outbursts. There can be a contribution from a hot component, and also there is a contribution of the nebula. So you are not able to that easily distinguish between these components of radiation in the optical part of the spectrum. But yeah, we had this advantage of having covered also the infrared part of the spectrum.
Thank you. I see no other questions, so thanks very much for your talk, and let's move on to Michal now.
Okay, so can I start? Do you hear me?
We hear you fine.
Okay.
You have 15 minutes. I'll give you a warning after 10.
So my name is Michał. I'm currently a member of Star Formation Group at Konkoly Observatory in Budapest, Hungary. So in this talk, I would like to tell about our searches of new young eruptive stars among Gaia alerts. So when we talk about eruptive young low mass primary sequence stars, we usually mean about F Orioni and AX Lupi type stars. These two classes are very similar in outburst amplitude, but F Orioni types outbursts last much longer, about 100 years. But in case of AX Lupi type stars, the outburst durations is about 1 month or half a year. So in fact, we talk about eruption and outbursts, but nothing here is destroyed. So in the picture shown on this slide, I showed the usually best probably mechanism which is leading to F Orioni type outburst. So on the right hand side of this picture, we see a typical classical Tauri type star in quiescence. Its inner disk part temperature, effective temperature is about 1,500 kelvins. But once, because the disk in the around young stars are unstable and there are many dusty clouds orbiting around them, once some massive clamp is injected into the disk, it adds some mass to the disk, which needs to be accreted onto the star. And as the result, the inner disk temperature rises up to 6,000 kelvins, and the star is brightening. This is what is called the outburst. And such eruptions have major consequences for disk temperature and evolution of the stars itself. And so filter observations obtained in broad spectral range help to understand a variety of major issues like the luminosity problem, which can solve the not efficient mass of stars, and F Orioni type outbursts can explain up to 10% of mass, which is added during the classical Tauri type star. The mineralogy of protoplanetary disk, architecture of planetary systems, and eventually establish initial conditions for life creation. So according to the most recent publication about these objects, only about 30 eruptive young stars are known. So given the variety of mechanisms leading to enhanced accretion and manifesting themselves through different rise times and outburst amplitudes, and also the most basic evolutionary questions highlighted above, the relatively small number of known sources makes high demand for discovery of new cases. And previously the stars were searched using Gaia, using ground-based surveys like dedicated surveys of star-forming regions. And as the time progressed, the Gaia Alert Science Alert 2 became a rich database to search for additional eruptive young stars. And the first discovered object was Gaia 17 BPI. And In our group at Concorde Observatory since 2014, we are regularly checking for new Gaia alerts for pre-main sequence stars, which show gradual light increase by a few magnitudes.
Sorry, Siegfried, can you mute yourself, please? We're getting interference.
Because
Thank
I'm
you.
not sure if I'm talking or not. Yes, can I continue?
Yes, continue, is muted.
Because I was not sure if I'm online or not at all. Okay, so once we identify a promising candidate in the next selection stage, we do the following. Like first, we try to associate the candidate with known star-forming region. Then to verify whether it has infrared access typical for young stars with protoplanetary disk, we construct its spectral energy distribution and color, near-infrared color diagrams, usually based on archival data. And we also, in the next stage, we examine optical and infrared light curves, mostly based on public domain surveys. And also we examine photographic plates. A certain number of candidates don't survive these steps because sometimes it turns out that some of the stars don't have near infrared access typical for protoplanetary disks, for example. So for those stars who survive, we start regular photometric monitoring in optical bands by 1 meter class telescopes at Piszkesteto Observatory in Hungary. Recently, I also added Montsuchara Observatory in Poland and one in Turkey. And we are writing proposals for photometric and spectroscopic observations in near infrared using NOT telescope at La Palma to properly classify nature of the outburst. We are searching also for information about morphology and variability of H-alpha line based on low resolution spectra obtained in collaboration with some of organizers of this workshop. And for finer sources, we use, at least we try to use TNG telescope in collaboration with Teresa Giannini and Brunella Nisini, and GTC, Gran Canarian Telescopio, in collaboration with Spanish astronomer David Garcia. So the first discovery published by our group is Gaia 18 DVI. It was published in the last year. Here I show the example of color magnitude diagrams in optical bands, which show that the star on the V-R and V diagrams moved from quiescence to the outburst on the patch which is different than the decreasing extinction. And on the right-hand side, we show the position of the star before and after the outburst, which is typical for for young stars. And here is also an example of spectra, optical spectra of H-alpha line, which shows either this spectrum shows H-alpha light either in absorptions, or it shows also sometimes PET Cygni profile. This is typical for what is seen in other FU Orioni type stars. Here we see an example of near infrared spectra in JHK bands, which show some most important indicators of FU Orioni class, like COE and absorption, which is typical what is seen, for example, in FU Orioni. And on the bottom, I show optical Gaia light curve of Gaia 18 DVI, and also optical results of our optical monitoring, as well as WISE data obtained in 2 bands. So one of the major results of this discovery was that the brightening in infrared bands started earlier, few years earlier than in optical, which is probably which it is not, there is not consensus within our group even, but it can be because of the accretion of clamp at about 0.5 astronomical unit, which is, and the mass was gradually moving toward the star, and the optical brightening started later. This can be the possible explanation. So we are also currently working hard on other promising sources, like those are shown on this page. On the left-hand side, we see the most up-to-date Gaia light curve. There are the green points and WISE data. They also show that the brightening sometimes starts only in optical bands. Sometimes the WISE data are almost constant. This source, the source in the middle, is the most promising one currently. When we
10 minutes, Michal.
When we obtained 2 spectra, and in accordance with our expectation, H-alpha line emission, the strength of H-alpha line emission is decreasing as the outburst is getting brighter. And we also investigate other stars which are promising X-ORI candidates, especially that one, which has shown one outburst at 2012, which is not shown here, but we examined pan-source data which show brightening during this time, and also nice PET-Signy profile. We also probably identified new intermediate cases between viewers and exors. I don't like to go into many details. And some peculiar cases which show sometimes only constant brightness in infrared and outburst in optical bands, or constant brightening, fading in optical bands and brightening in infrared, as well as similar amplitudes in infrared and in optical bands as well. Okay, thank you for your attention. If you have questions, please give me.
Thank you very much for your beautiful talk, beautiful data. Really impressed. If you have questions, please post them in the chat or raise your hand. So I will ask a question. I'll take prerogative. So there are a couple of things that look like they're becoming a mystery, which are quite interesting, which is what's happening in the WISE bands and the infrared compared to the optical. I thought it might all be easy and they all do the same thing, but you seem to have a diversity of behaviors. Can you speculate at all?
I think this is the matter maybe of of unusual extinction, because we often assume the mean extinction law, but this is what I think now. But we didn't really arrive to conclusion within our group what is going with those sources. And we probably need more data, like spectra, etc., because based just on light curves, we cannot differentiate between many possibilities. Yes. So these stars should probably will be observed soon during our program. Yeah.
Great work. Thank you.
Thank you.
Pavel has a question for you.
Yes.
Yes, thank you very much, Michał. Are you planning to use spectra in infrared to constrain the nature of these targets, because they should be helpful comparing to the optical?
Yeah, because I forgotten to mention that some features which are visible in absorptions are common for F-Orioni type stars, but for X-Lupi type stars, the same features are seen in emission. And this is probably at least in the early stage of our investigation, this is the main criterion which can allow us to classify properly the source and make expectations about outburst duration and so on to plan properly the observing campaign. because I forgotten to say, but it is also important to mention that many of these sources are planned to be observed by ALMA or NOEMA to follow mineralogical changes in the disk. So we have to know in advance what to do. So almost up to, we have to be up to date what is going with the sources, because yes.
Nice, thanks.
Before, if you don't mind stopping sharing, then Artie can get his slides on. Michał, are you confident in the classification of 18 DVY, 18 Davy? Can I update it on our website as a confirmed FURIONIS?
This was published, and the star is continuing. It is slightly fading, but not that much. This is rather typical for F-Orioni type stars.
Great.
Of course, in next year, after a year or so, it might turn out that the star is starting quick fading, and this would be the case of intermediate. This may turn out to be an intermediate case between FURs and EXOs, but we'll see. We cannot speculate.
Okay, we leave it as a note then, rather than a firm classification. Thank you very much. Artie, if you're ready to go, you've got 15 minutes. I'll interrupt you. Well, I'll give you a warning, a verbal warning after 10 minutes.
I have to make sure I unmuted myself.
We can hear you.
Thank you for inviting me to give you a talk introducing our telescope at the Töringen Landessternwarte, our 2-meter telescope, and highlighting its use for primarily for targets of opportunity or rapid response. And then this first view is one target of opportunity. This is actually an image of Gaia that was taken with our Schmidt camera. And here you can see this little streak here. That is Gaia in orbit. We have several telescopes at our observatory in Tautenberg. The main one, which I'll be talking about, is our 2-meter Alfred Jentsch telescope. Alfred Jentsch was the chief designer of this telescope, but we also have a 30-centimeter semi-robotic telescope, as well as a LOFAR radio station. And here you can see the LOFAR field with the high-band antenna field, and the low-band antenna field. And of course, it's part of an international LOFAR telescope spanning all across Europe. And you can see, maybe those of you at the back of the auditorium won't be able to read, but this is Tautenberg, the radio station. And we were actually the second international LOFAR station that was commissioned. You may well ask, I mean, our observatory is located in the middle of, in Germany, in the middle of Europe. And you may well ask, well, what kind of a astronomical site do we have? And the short answer is it's not bad. I mean, here's a nighttime image of Germany, and the star roughly marks the location of the Tautenberg Observatory. And the skies are reasonably dark. This is a view from the all-sky camera, which shows that when it's a new moon, you can clearly see the Milky Way every night. And I've compared here Tautenberg to a first-class site, La Silla. And basically, we get roughly half the spectroscopic nights of La Silla. Our seeing is twice as bad, and our sky is roughly 1 magnitude brighter. And so the upshot is La Silla is twice as good a site, better than Tautenberg, but at least 5 times the operating cost. So we are a much more cost-effective observatory. The advantages of our 2-meter telescope is that most of the time goes to the scientific staff. We have 8 permanent scientists, and the schedule is literally made a few weeks in advance, and it's very flexible scheduling, and new observations can be inserted pretty spontaneously. I mean, you just send an email to the observer and say, hey, can you observe this object tonight? It's pretty interesting. And some of the science programs in the area of what I call rapid response or targets of opportunity, and I'll highlight some of these. It's gamma ray burst follow-up, near Earth objects, the follow-up of test transit candidates. This is our exoplanet work, And sometimes we participate in multi-site campaigns. Now, our Schmidt camera, we have a huge 1.34 meter diameter corrector plate. And in the Schmidt mode, it is the largest classic Schmidt telescope in the world. That's the biggest corrector plate in the world, I'm pretty sure. And the telescope, it's so big you can actually walk in to mount the Schmidt camera. And we've installed a new CCD, which is a 6,000 by 6,000 pixel device. It's huge. I mean, this is 10 by 10 centimeters, which gives us a 1.3 by 1.3 square degree field of view. And this is definitely a big upgrade from our previous CCD. And so this is an image taken with the new Schmidt camera called Taucom. And this is the diameter of the moon. And this square is the size of the old CCD. And you can see we have a lot of CCD real estate and a large field of view. So the gamma ray burst effort is led by Silvio Closa, and he prepared this view graph for me. I mean, the advantages of our telescope is that it's at a nice geographical location and longitude. It's relatively large aperture for such a large field of view, and it's really prepared for doing target of opportunity runs. And here, this is just an example of a gamma ray burst where there was a follow-up. They detected the afterglow on the Palomar 48-inch, and this was 30 minutes after the burst. And then 12 hours later, we tried to observe it from Tautenberg, and there was nothing there. It rapidly faded. And getting good light curves of gamma ray bursts, one important thing that you can do is detect a potential rebrightening of the afterglow due to a possible supernova component. And as you might guess, it's very difficult to get redshifts for gamma ray bursts. And one of the tricks you can use is if this is really due to a supernova component, you can take light curves of known supernova, redshift them by an amount and see if it could match this turn up. And here you can see that maybe this is a gamma ray burst at redshift of 0.5. And of course, in the future, we're going to be looking at the Fermi error boxes. And part of this is also for gravitational wave detections. If you detect a gravitational wave event, then we try to go see if there's any optical components. Now, it's worth mentioning the logistics that we do for these gamma ray burst events. And basically, we know we have a GRB event that typically comes from the Swift satellite, and it sends an SMS text message is sent directly to our telescope control computer. It calculates the visibility. If it's not visible, then, well, you just continue your normal observing. If it is visible, then a pop-up window occurs on the observer's computer. And at the same time, an SMS text message is sent to the gamma ray burst team member, in this case, Silvio Closa, who essentially is now becoming the observer. And here, this is the only human interaction where the observer, decides if there's a go, no go. Maybe the transparency isn't so good, but if it looks good, you press a button, and the telescope automatically moves to the GRB events and starts the exposure, and the observer has to do nothing. If the observer decides not to go to the GRB, then he or she better prepare a good excuse to the GRB team why you didn't observe it. And trust me, this is it's the human element that, I get Silvio coming to me and saying, why didn't they observe my gamma ray bursts? And, it's a typical thing. It's hard for an astronomer to stop your own program to observe somebody else's target, but it works pretty well. Another thing that we do is near Earth objects, and this is something that the public can readily grasp. I mean, we're doing our part to defend our planet against cataclysmic events. And the purpose of this is basically to find all the near Earth objects and determine orbital elements to find those that pose a threat to Earth. And so this is a program done by Bringfried Steklum, funded by ESA. Of course, ESA is very interested in this kind of stuff, as well as NASA. And here, this is the number of measurements we've taken of near-Earth objects. And we got the new camera here, which greatly increases the number of our measurements. And here, this is a recent one from a press release. We can see here's the near-Earth object. And this was an important measurement because with this measurement, we could refine the orbital elements and determine that this NEO did not present a threat to the Earth. It was a close call. It may have been a threat, but now the orbit has been determined, so it's not a problem. Another mode that we have is what I call the mosaic mode, and Eike Günther is actually doing this to survey the entire TESS northern sectors, which is in the TESS continuous viewing zone. And the mosaic mode it's rather nice. You basically give it a size of a field of view and a central coordinate, and the telescope just goes off and does the mosaic, getting images covering the entire field, including some overlap. Now moving to the Gudea shell, which is my favorite instrument. Here I am pointing this lovely spectrograph. Here's the camera. And here's Eike Günther, a young Eike Günther. Also, you can see here's the shell in the background and the grisms. And it's a cross-dispersed shell. And these 3 grisms gives you this wavelength coverage, high resolution, 67,000 resolving power. It is
10 minutes,
Archie. iodine cell for precise radio velocities. This is a cell, not the cell we use. And this iodine gas, starlight goes through it, and the iodine absorption lines impose our wavelength reference for precise radio velocities. And on a bright star like Beta Gem, we can get down to 2 meters a second. And here we see the pulsations of Beta Gem. And even without the cell, we can get pretty good precision. This is an 11th magnitude Cepheid, which has the RV curve has a scatter of less than 200 meters a second. We're using the telescope for follow-up of transit candidates from TESS, the NASA mission. And of course, a candidate's only a candidate until you get a radial velocity curve to determine the mass. And here are measurements for a brown dwarf. And here are measurements along with McDonald measurements of a 2 Jupiter mass planet. And both of these are in very short orbits. And that's actually a pretty good niche for our telescopes to investigate giant planets and brown dwarfs, because all the resources now go to looking for small planets, and these objects are often ignored. And in the mass density diagram of planets and stars, you can see the brown dwarfs up here and the giants here. They all fall along this a track, and there's no distinguishing features between giant planets and brown dwarfs. But if you look in the mass distribution, there's a bimodal distribution, which may indicate 2 different types of mechanisms, and these may separate the brown dwarfs from the giant planets. But of course, these are small number statistics, and getting more of these objects, which is what we want to do, will help us determine the difference between planets, giant planets, and brown dwarfs. As I said briefly, we can use it for multi-site campaigns. And here, this is a campaign on Procyon, and the dark measurements, these are radial velocity measurements. The black points are those that we've taken from TLS. There's a multi-site campaign, and you can see we do provide useful longitude coverage. And then I want to end by showing a nice example for using both the Schmidt camera and the shell spectrograph. This was the very famous supernova in M101 that occurred almost 10 years ago. And these are our Schmidt images showing the supernova 211 FE. And it was bright enough, I think it was around 11th magnitude, which means we could actually get a high resolution spectrum of this supernova, and this was taken with our shell, beautiful spectrum. But this is the kind of stuff we can do. And then just coming quickly to my summary, I mean, we have a 2 meter, in Schmidt camera, it's 1.34 meters. In the shell spectrograph, we remove the corrector lens, and it's really a 2 meter telescope. And it's routinely used for follow-up targets of opportunity. We have flexible scheduling, a nice location in longitude for multi-site campaigns. And our key programs for these targets of opportunities are exoplanets, gamma ray bursts, and near-Earth objects. And the final point I want to make is, this is a nice facility if we want to play a role in the follow-up of Gaia results, alerts. This is things that we're kind of geared to doing. And with that, I'll entertain questions. Thank you.
Thank you very much. That's a beautiful telescope. And I'd be very happy to talk more about things we could do. I see a question from Pavel. Go ahead, Pavel.
Yes, hello, Artie.
Hello.
Nice to see you. Yeah, this telescope is great, and it's really big in diameter, so it seems to be perfect for faint photometric observations of faint targets. But what about the spectroscopy? What is the limiting magnitude for your Eshel spectrograph?
Of course, it depends on your signal to noise. If you that 11th magnitude Cepheid, that we got signal to noise of 100 in 1 hour, and so the really 13th magnitude is about the faintest we can go. We're wanting to upgrade our spectrograph with the fiber feed and go fainter, and maybe getting a commercial adaptive optics systems to improve the image quality. But currently, 13th magnitude for a usable spectrum, and 11th magnitude if you want to do stuff like radial velocity measurements.
I see. Yeah, I was wondering rather on the classification spectra. So we don't need high resolution actually. But just lower resolution, but for fainter targets would be.
We do have a low resolution spectrograph on the Naismith platform, but it's semi decommissioned. No one uses it, and it's not the most efficient, but it is, and it can go down to 18th magnitude for low resolution spectroscopy.
Wow.
But it's not used that often, because if you mount it, then you're stuck with using that throughout the period. And most of our users are either Coudet or Schmidt observers.
Yeah, especially in the era of TESS, I imagine.
Pardon? Especially
in the era of TESS, I imagine this is a strong program.
Yes. I mean, TESS was sort of, and it was a godsend to us. And then we have Plato coming up, and Plato will be much better. I mean, that was the problem with Kepler and Corot. The targets were just too faint for us. But TESS and Plato is kind of stuff we can actually make a major contribution in.
Yes. Thank you very much, Artie. If you wouldn't mind stopping sharing.
Stop the share.
And then class can start to share. You see your camera. You see a slightly chopped off slide.
Yeah, sorry about that. I'll go to the full screen. Can you see that?
Yes, that's perfect now, and excellent. I hear you fine.
All right, thank you.
You have 15 minutes, so I'll give you a warning after 10.
Cheers. Yeah, so my name is Klaas Wiersma. I work at the University of Warwick, and I'm going to show you some work that we've been doing over the last few years with one of my PhD students on polarized light in optical transients. And this is work done in a very large collaboration, and I listed some of the names below, but it's probably quite incomplete. But I thank everybody who helped me with this. So as you all seen in the last few talks, there's definitely a change in the ecosystem of transients that we're seeing now. And that's all made possible by new facilities. So we can see fainter transients over a wider wavelength range, all the way from low frequency radio to TeV emission. The detection rate of transients is going up. The timescales at which we can probe transients increases in both directions. So that opens up a lot of new opportunities. And I think there's an increased interest in doing large samples well with statistics that you can actually use. And that gives us some nice opportunities. So one of them, of course, is multi-wavelength perspectives become easier. If you can serendipitously detect in the radio, say, a lot of Gaia transients, then that opens up a lot of simultaneous work that you can do. I think spectroscopy is changing in a sense that currently the completeness is not so bad for bright sources, particularly in the Northern Hemisphere. The CTF team in particular has been working very hard on that. But as rates increase, that will become harder. Multi-messenger astronomy has arrived. We can see neutrinos and gravitational wave now of transients. And of course, infrastructure to make new things possible, like brokers and event handlers and TOMs and so on, have come to the scene. And I think the keywords really for transients in the new era are context, added value, and availability. Now let's talk a little bit about observables. So for each transient, you can place in a very large parameter space with lots of axes. For example, the optical flux, radio flux, X-ray flux, high energy emission, astrometry, polarization degree and angle, and all of those, of course, as a function of time. So each transient lives somewhere in this large parameter space. And you can make plots of slices through that parameter space, such as this one. This is from the Athena XIView book. And here the typical time scale of X-ray transients is plotted horizontally versus the peak X-ray luminosity on the right-hand vertical axis. And you can see that sources sort of find their way in these clusters of data points, really. And of course, you can add axes to this. So on the left is the absolute peak magnitude in the optical. So you can see where a source falls in the X-ray optical timescale domain, for example. And even doing single snapshots, where you have only one data point for a given transient, is already useful, because you can see where it falls in this diagram and where it perhaps falls into a part of parameter space you haven't really looked at before. You can do it in the radio as well. Here on the right is a diagram where the optical flux density is on the horizontal axis and the radio flux density vertical, of quasi-simultaneous measurements. And if you plot any transient that you can find in this diagram, you'll see that they neatly separate out in clusters in this blob of points. But of course, each transient moves in this diagram as a function of time. So rather than just throwing them all on as blobs, you can also look at the tracks that they make in the diagram like this. That is done on the left-hand plot, where the same axes are used. And you see for a couple of interesting transients how they walk in this diagram. Now, theory tells you how sources should walk in this diagram and where they should roughly cluster. So you can compare your measurements with what theory tells you where your sources should be and should move as a function of time. And that way flag up interesting sources in these sort of diagrams. Now, these are just a couple of more or less randomly chosen parts of parameter space, but you can slice along any axis that you want, of course. Now, in this talk, I want to focus a little bit more on the optical polarization degree and angle as an interesting discriminator for large volumes of transients. So what could reduce polarization in the first place for transients? I listed them sort of in order of my interest in them, but of course, your interests may be quite different. So first of all, you can see polarization that is induced by dust along the line of sight in our own galaxy. Then we may see polarization induced by dust in the host galaxy or near to the source, very close to the source. And we may see polarization intrinsic to the source emission itself. Now, all of those aspects are interesting, but perhaps some of those are more interesting than others. So on the first thing, polarization induced by dust along a line of sight in our own galaxy. So this is caused generally by dichroic extinction and scattering by non-spherical dust grains with a preferential alignment. So some of the dust grains are preferentially aligned in a certain direction that produces linear polarization. And this is an interesting thing to study because it's the key foreground in cosmic microwave background surveys where this dust emits microwaves that are polarized because of this same alignment process. And what we can see there in emission, we can compare to what we see in transients in transmission. And that's a very interesting thing to do. Now, on the second topic, polarization induced by dust in the host galaxy or near to the source, well, we all know that for a lot of progenitor objects of transients, dust is a really important thing. So an obvious case is the dust shells around our corona borealis stars or embedded transients and so on. And of course, by studying dust polarization properties for extragalactic transients, you may learn a lot about star-forming regions at high redshift or things like that. The third topic, polarization intrinsic to the source emission, there's various processes that play a role. The geometry of the emitting regions, for example, plays a role in how much polarization you may observe or not. Whether there's a non-thermal emission present, like synchrotron or Compton emission. And of course, the order and the strength of the magnetic field in the emitting region. And of course, for many transients, you see a bit of a mix of emission processes. You may have an accretion disk with a jet, for example, and when the balance between those emission processes changes, you may see polarization emerge or go away. Now, for each wavelength, you can make a list of these sort of things. But what it always comes down to is that a lot of the physics that we see in polarization space does not map well on light curves and spectra. So it's important to bear that in mind because we can learn a lot of unique things from polarization data. Now, just to give you an example of a source that's of particular interest, this is AT2018 COW. I think it's been mentioned before in this conference. It's a very peculiar supernova-like source, which showed very bright radio and hard X-ray emission, which is not normal. And in the optical, looked like a peculiar supernova. Now, these strong emission processes in the radio and the X-ray also translate in a polarization degree in the optical that we detect for this source. So while this source may have looked a bit odd in spectra as well, if we had no spectra for this source at all, we would have still seen it as being very weird in imaging polarimetry already. So this is just an example where a multi-wavelength perspective can give you something you didn't expect to find from the optical alone. Just to make sort of the point of these walks more obvious, these are two, I would say randomly chosen, but that's not true, two nice cases of transients. On the left-hand side, a well-known X-ray binary in outburst, 1820 plus 070. I think many of us would have observed it. And on the right-hand side, the cow again. And in both plots, I plot a measure of the X-ray brightness, a measure of the radio brightness, and a measure of the optical brightness along the axes. And the size of the data point is the linear polarization at the time. And you can see on the left-hand side with MAXI, you can see a clear state change in the X-ray binary. A jet is emitted. That gives you the big bump in the radio, but there's no strong response in the polarization. That tells you that the polarization in this case was dominated by dust and by emission from the accretion disk. On the cow on the other side, on the right-hand side, you see a fairly monotonic decay in brightness in X-rays and in optical, but a very marked change in polarization degree after a few days, which is very odd. So these are just two examples of walks in this multi-parameter space that you can look at. I'm going to skip this for sake of timekeeping and go straight to this one. So you've seen this kind of plot before in the X-rays, but now I do it in the optical in the left. So on the left is on the vertical axis is the absolute magnitude in R band, and on horizontally is the typical variability timescale. Now you might recognize this plot because it's from the LSST handbook. I just changed the colors of it. And you can clearly see that different kinds of transients cluster in different locations in this diagram.
That's 10 minutes class.
Thank you, yeah. And we can make a very similar plot on the right-hand side by plotting the degree of linear polarization in the optical on the vertical axis. And again, you should expect some some clustering going on there. It's important to note that for many of the sources that source types on the right-hand side, our knowledge of the polarization is extremely limited. We have maybe 3 or 4 cases with any polarimetry at all for some of these classes, whereas others are very well studied, like supernovae and blazars. So we decided a few years ago to undertake a polarimetric survey of transients using the NTT at La Silla, using EFOSC and SOFI, instruments well known, I think, to the transient community through Pesto. And that worked quite well. So we randomized our targets. We observed random transients with no requirement of spectroscopic typing beforehand. The only thing we wanted is that they were brighter than magnitude 20.5, because the magnitude 20.5, a polarimetric measurement takes about an hour. So it's similar to spectroscopy timescale, really. We did snapshots only, a single exposure in V-band. And we observed about, I think, 80 or 90 sources in total. Our aim was 75. Unfortunately, we got really rubbish weather, but that's something you can never quite change, can you? And a subset of our sources was observed more than once, and a subset we observed with 3 filters rather than 2, rather than 1, so that we can make some proper statistical inferences. You can see a distribution of a subset of these, the first year run, in the bottom right. So we can see sources over a wide range of polarization space and a wide range of timescale space. So this worked. We already found quite a few sources we didn't quite understood existed, like quite strongly polarized, very young supernovae, for example. So we learned quite a lot about how should we do such a survey if we want to do this in a large scale in the LSST era or the CTF era, really. And one of the things that we learned is that taking humans out of the loop is really helpful because humans make decisions that are not always very easily caught in a prior distribution. So we've now moved to a survey called the RoboSplot, where we robotize all our follow-up decisions and run it on the LT, which is robotic in nature anyway. And we particularly look there for young transients with coming from CTF. And in the future, we'll be rolling out a survey called Pepper, which is a scaled-up effort named after Sgt. Pepper, because a lot of the Liverpool telescope instruments and surveys are named after the Beatles. And that will hopefully do about 100 or so transients per semester, brighter than about magnitude 18.5. In the future, we're working hard on consolidating a lot of our individual science programs on 8-meter class telescopes into a wide umbrella program to provide some critical mass at ESO, for example, to think more seriously about time domain polarimetry. And that is progressing fairly well. In the meantime, we try to recruit as many observatories with polarimetric capability into our network as we can. And that's working fairly well so far. And here at the end with a quick announcement, is that we are organizing a conference, hopefully, in September in Italy on astrophysical polarimetry in the time domain era. This was supposed to have taken place last year in September, but for corona reasons could not happen then. And we're keeping our fingers crossed that maybe this year it can take place. And if you're interested in doing transients in any kind of polarimetric way, as in optical, radio, or anything else, then please consider attending this conference. And I'll end there. Thank you very much.
Thank you very much, Klaas. So I'm not seeing any questions. I'm also conscious it's lunchtime. It's been quite a long morning. Okay, so then I think it remains to me to thank all the speakers that we've had today in our 2 sessions. It's been really, really fascinating throughout. Thank you all for presenting your work, for attending and listening so diligently. I'll hand over to Łukasz, the organizer, who may have some announcements.
Yes, thank you, Simon, for chairing this session, and thank you to all the speakers. I would like to remind you about the Wonder Me room we have reserved for you, and it's open 24 hours. You can meet there at your convenience and talk to people. And also, I would like to remind you that tomorrow we start at 3 p.m. Central European time, and the agenda is available on the wiki page, and all the links to YouTube as well. So thank you all for joining today. See you tomorrow, or see you at the Wonder Me space. Thank you.